Hello there, thank you very much for joining me again today. Das ist good. Das ist ROHDE SCHWARZ CMS33 Radio Communications Tester on the bench for review, stripped down, comprehensive look internally and externally, features. We're going to go right the way through it, including all the accessories. We're also going to learn about some of the optional features that are on this radio test set, which aren't found on many other radio communications test sets in the marketplace even today. This particular radio test set is a model CMS33, and it's very similar in design and function to the other ROHDE SCHWARZ test instruments in the CMS range, such as the CMS52 and the CMS54, which we've done repair videos on in this channel. So sit back and enjoy. We're going to have a look at this instrument. We're also going to learn about the Avionics side as well, which are options that are fitted on this for VOR and ILS. Now, VOR is a VHF omnidirectional range beacon, which basically allows aircraft to navigate basically, and ILS is instrument landing system, and this test instrument was designed to test those systems on aircraft. So it's obviously quite a very important high specification test that needs to be done, and if you get it wrong, naturally the consequences can be really severe, as you no doubt can imagine. So this test set has that feature on it, so both those features can be tested using this test set. So we'll also have a look at that in depth. We've got the manuals as well with all sorts of in-depth information. We've got accessories as well which connect in the back, which we'll go into later in the video, and we'll have a right way through look at this radio test instrument, including its use in transmit and receive measurements, not just in avionics circles but also in AM and FM modes. It has SSB, it has all kinds of test features on it we should expect on a high-end radio tester, which this is. And we'll go right the way through it and have a look at all its features, and let's see where we get with it. Okay, so we've got the radio down here, transceiver plugged in, and we can do some tests now and show you the features, run through all the parameters and everything, and how to set this test set up. Now, for those that don't know, ROHDE SCHWARZ have been around since 1932. The company was founded by Lothar Rohde and Hermann Schwarz, who formed ROHDE SCHWARZ Partnership as a company in 1932. Now, ROHDE SCHWARZ, they're an international electronics group, and they specialise in the fields of electronic test equipment, in broadcast media, cyber security, radio monitoring, things like spectrum monitoring, radio location and radio communication systems, as per this test set in front of you. But they've got quite a foothold in defence market, PMR, aeronautical markets, marine, everything really. So they're a very big company, been around for a very long time. Okay, so looking at where we're at the moment, I just want to show you some of the ROHDE SCHWARZ, what I call quirks. And you'll find this on most ROHDE SCHWARZ instruments. They tend to operate just ever so slightly different from the conventional norm with other radio test sets, such as HP Agilent, Keysight, Marconi, IFR, Aeroflex, Cobham, and then obviously things like Anritsu, Advantest, Rigol and Fluke, and other manufacturers of test equipment. They all tend to have a very common user interface, whereas on the ROHDE SCHWARZ test set it's a little different. For example, under TX test here, for example, I'll just turn the volume down. The test set automatically defaults to AM demodulation in this case, because I've done a master reset earlier. Now, sometimes on some test sets you'll press the demod button, and then it'll give you the options then in order to be able to see the difference between AM and FM sidebands, that kind of thing, and it'll be available under the demod button. But here, as you can see, it doesn't give me that option even when I go into the sub-menu, which I'm going to show you to navigate that shortly. I don't get, although I get an FM depth selection, I don't get FM as a mode to select. And this is a little different on these test sets to what it is on other brands of test instrument. And how that's changed is quite simple. What we do is we go to the RX test, and because the RX test is in AM, because we've got 30% modulation instead of FM, we have to change the RX test to FM before TX test will then change with it. So it's a global parameter within the RX test which has a direct influence on the transmitter test. So I'll demonstrate that now. If we go to AF1, which we're going to leave at 1 kHz, we'll select mod 1, and this time we'll enter in 1.5 kHz. Now it's changed the test set, receive signal generator, to FM. That now has a direct bearing on the TX test, because now when we go to TX, the percent field is now being changed to kilohertz for the modulation of the transmitter monitor. So that can be a little bit strange for some people, and they'll be thinking, oh, you know, I'm pressing the DMOD button but I'm not getting anywhere with it, and you know, and then they start scratching their head. But it's little things like that. Another thing as well that I want to show you regarding the ROHDE and SCHWARZ quirks is you'll find that in most menus you'll select, and this cursor moves with it. Obviously, as you can see, this little black cursor arrow moves with the field. What you'll find as well, if you look here, there's a little arrow that points down. Whenever that appears, that means there's a sub-menu within that setting. So because we've currently set the transmitter monitor to counter, frequency counter mode, where when I press the transmit button on the microphone, the test set finds the frequency automatically and reads the power. It also has many other features within that parameter. And how you access that is down here in the bottom right hand corner. There's a down arrow button and an up arrow button for the menu. And this is the strange thing about ROHDE and SCHWARZ, which you don't tend to find this on most other instruments. But what you do when you see that little arrow and you're on a parameter, no matter what parameter you selected, whenever that arrow's available, it shows us as a sub-menu. So now when I press that little down arrow, we suddenly get other features which come under the parent field of counter and set RF. So suddenly we've got things like, for example, frequency preset, correct count, or I think that's what, direct count, sorry, frequency trans, things like that. And they appear in a slightly different sort of a bold italic, but with a slanted italic on them, and they're slightly different, so you can see the difference between the parent menus and fields versus the sub-menus. Now, if there's multiple pages or multiple fields, then the arrow will keep displaying. As you can see, the arrow's disappeared. Now, that means, obviously, when we go back up to the main menu, the arrow will appear again. And it doesn't matter whether you go to the, in this case, the power or ACP field, for adjacent channel power. If we press the down arrow, then we get things like, for example, peak envelope power for things like AM and SSB modes, the time. So basically the time in this instance would allow us to, for example, when you're speaking into an SSB radio, because the carrier is suppressed, the RF energy is going from basically nothing to a peak power, whatever that might be, say 150 watts. And the test set, if it's left in frequency count mode, has got to try and lock onto that frequency, demodulate it, and then display the measurement. And the thing is that as the RF power is jumping up and down with the modulation, the test set's got to try and chase after it to lock onto it and then display the analysis of the measurement. And so when you're measuring SSB signals, you need to sort of soften that process, and that's why we've got the time here, auto, fast and slow. Naturally, if we're modulating an SSB or an AM radio with a 1 kHz tone and the tone is constant, then obviously the RF power will be constant, and also the measurement will be more stable. So that's where we get the little time measurement there. Then we've obviously got the power hold, so we can hold the peak RF power, for example, on transmit for both AM and SSB. And then obviously we've got power hold resolution as well. So there's all kinds of different things that you can go into just in that one measurement alone under power. So if we go back to the parent menu, again under DMOD here, if we press the down arrow again, then we get far more options. Again, there isn't another menu below that because the down arrow hasn't appeared. And again, we can go to decode. The down arrow's appeared again, so we can press the down arrow, and now we've got these parameters, and which we'll go through as part of this video. Again, down arrow appeared again, and we've got different filters. Notice the down arrow is still on, so that indicates that there's another field beneath this. So we can press that, and then obviously we've got those. I'm not sure if there's another field if it goes back now. So there's two sub-menus in this particular option. So under filter, there are two sub-menus, whereas the other measurements that we were doing earlier, the parameters, only have one sub-menu. Again, same here, down arrow. We've got more parameters there. So, and this is how you work the test set, basically. It doesn't matter whether in RX test or in TX test. It's a little strange, is that that's how ROHDE and SCHWARZ get you to check, further parameters within it. On most radio test instruments, such as the Agilent, HP radio test sets, IFR, Aeroflex, Marconi, when you select the field, normally then you would have the options displayed. You have the buttons that say this is a field I want to do, and then, but what it is that the way ROHDE and SCHWARZ have done it, you select the field, you change the parameter, the parent parameter, in this case the RF frequency, but when you've got the little down arrow, you press the down arrow, and then you get some more features. So it's quite easy to miss that if you don't know that about ROHDE and SCHWARZ, and you can miss out on a lot of features because there's a lot of spec on these machines. They are very highly specification when it comes to the quality of the instrument with regards to all its sub-parameters. There's a lot of functionality there that the test set will have that you might not realise until you go into that sub-menu. Another little thing that I quite like about the ROHDE and SCHWARZ test set, if it doesn't have duplex on it as a option, when you're in receive test, when you cue up the microphone to transmit, the test set can detect it. You can set the test set so that when it detects an RF carrier, even when it's in receive signal generator mode, what it will do, it will automatically flick to TX. So you're not having to go between the TX and RX functions, if you like. You can just basically set the parameter so that when you key up on the radio, it automatically flicks like that to TX test, and then when you unkey the microphone or the transmitter, it goes back to RX test. And I quite like that because it saves a lot of manual faffing about by pressing the button on the front of the test set. So that's a little example of another little feature. But it doesn't matter whether you transmit fields or receive fields. Whenever you see that little down arrow, then there's other options available. So that's one thing to note about the ROHDE and SCHWARZ. Okay, so what we'll do, we'll just go through the individual parameters now and show you that, and test this radio that we've got down here, and then show you the full setup of the instrument. Now, obviously, on this particular test set, we've got two RF inputs and outputs. Mainly, the N-type is the RF in-out. Obviously, that's the high power port, goes up to 125 watts, which is far greater in power measurement capability than the CMS33 Radio test set, which I've done a repair video of, where the maximum power on that is 50 watts. So this is more understanding, possibly because it's designed also to do SSB radios in the aeronautic, avionics side of things. So obviously those radios do quite a bit of power, so that's probably why it's rated to 125 watts. Although I can't understand why the CMS33 radio test set is only rated to 50 watts, and that does SSB as well as duplex, as well as other systems. So Seems a bit strange how they've got a fully featured radio communications test set, being the CMS34, that's only rated to 50 watts, whereas this is rated to 125 watts on the N-type, because it tells us here. And for the CMS33, one of the common misconceptions with these test sets is often these ports being close together are confused. This port here is actually an RF port, and we can select that for measuring transmit signals. It's not available in the receive field as an output, it's just an input as per the symbology here. But under TX test, for example, you can select between input 1 and input 2, input 1 being the N-type and input 2 being the BNC, and so we can select those between that. Now, this port here, I also find strange how ROHDE and SCHWARZ have legended the port in the fact that it doesn't tell you how much RF power that port can take. Now, most radio test sets, typically the BNC, being a low power input or output port, can only take a maximum of 1 watts radio frequency power. This doesn't tell you how much RF power it can take, and it tells you that it's a 50 ohm socket, it's an input, but it doesn't tell you anything else apart from it can take 1 volt maximum as a DC level perhaps, but it doesn't tell you RF power. Quite a lot of these test sets across the CMS range, often because this is a BNC connector without the information as to the RF power, simply implies that it's attracting people to connect to it and thus transmit from a mobile radio like this at high power into that port and then burn the radio test set out. Now, as we'll see later on when we strip the test set down and we have a look at its internals, the module which connects to this BNC socket has a pi attenuator made of surface mount resistors, and that's one of the grumbles I've got really with ROHDE and SCHWARZ test instruments, is they don't have an automatic disconnect relay to protect the RF port. When you look at most radio test sets in the radio frequency test instrument world, such as Aeroflex Marconi for example, when you feed too much RF power up the BNC socket on a radio test set in the Marconi range, it has a disconnect relay. It'll display a message to say warning, RF power overload, whatever, but what it will do, it will protect itself, it will disconnect the RF socket until such time as the RF power is removed, thus protecting the instrument and preventing damage. The ROHDE and SCHWARZ test sets don't do that, and that being this model as well as the CMS34, 52. So you've got to be really careful about this little port here, because it's so easy for the inexperienced to connect a 25 watt transmitter into there from a typical mobile radio, a marine radio or a ham radio, whatever, PMR radio, into there and below the test set. So that's where I'm a little bit, sort of confused as to why ROHDE and SCHWARZ chose never to indicate how much RF power that can take. Secondly, as well, it's in close proximity to the audio connectors, and the audio connectors themselves are not RF ports, obviously. So on most radio test sets, they keep the RF ports physically separated from the audio connections, and that's so you don't connect audio into the RF port and likewise RF up the audio port by misconnecting a BNC because they're in close proximity. Now obviously they've got an orange band here which seems to denote the fact that it's RF, but my own personal view is I think they could have done a better job in making it clear to the user that this is an RF port and what its RF power level rating is, and they don't seem to do that on the CMS range. Maybe they do now on newer test sets, but certainly on this model they don't. Okay, so we'll get into doing a RX measurement. We'll connect the audio up to the radio that we've got under here and connect it into the AF in so we can measure synad, and we'll set up the signal generator and get cracking and go through all the parameters. Okay, so just to run down the main parent menus, which is what you get displayed when you first turn the instrument on. This one here has auto test in the top left hand corner, as well as right up in the top left hand corner we've got RX test, which we can select. We can also go to TX test as well in the top corner. Likewise, when we're in a particular TX test, we can go to RX test as well, and vice versa to TX test. From the parent menu then we've got that selection in the top left and right corners. Underneath it's auto test. Now what auto test is, that allows us to create test programs for features of a test instrument that we can then store on a memory card or within the internal memory of the instrument, and then recall it and run it under the auto run. So for example, I can select DIR for directory, and then we've got, this is mainly to do with VOR and ILS, which is the aeronautical navigational aids and instrument landing system tests. So you can then run an auto test of those particular avionics test features. We've got, again, printer setup as well. You've got type. There's all kinds of things to do with memory cards. It'll now run a test if we wanted to get it to do that, to program it, where it'll send out particular functions, be it RF carrier, sending a particular locator beacon signal out, things like that. And once it's done the test, then it'll print it off for you. So that's the sort of thing that can do. Also, as part of this, we can go then directly to the parent menu, back to where we were. Duplex test, DX test. This option isn't available on the CMS33 unless you pay for it, but it is standard, I think, on the CMS52 and 54. I show that working on the CMS54 repair video. If you haven't seen that, please go and have a look. We've also got the Spectrum Analyser as well, which will feature in this video, showing you that working with a signal, a radio transceiver. And then we've also got SSB for single sidebands of lower sideband, upper sideband and CW modes. SSB is widely used in the HF bands, in particular with marine radio, aeronautical radio, for long distance communications, especially when aircraft are across the oceans such as the Pacific and Atlantic Oceans. They get so far across and VHF communications don't work, so they often go onto sidebands. That's great for testing military radio systems, AM radio systems, and other SSB radios such as survival radio communications, emergency beacons, things like that often work on sidebands for things like, for example, I forgot what they're called now. I'm having to think. Life rafts and things like that are on ships, lifeboats and things that are deployed in the event of a ship incident. Often those beacons work on upper sideband, lower sideband, and this test set allows that test to be functional. And then you can read the signals at those frequencies. A lot of personal navigational beacons and things like that for rescue, air sea rescue work on low frequencies. We're using sidebands for to allow rescue services to track you and obviously locate you, to rescue you, as well as radio communication systems. So the sideband option is obviously quite an important feature. And we'll go into that as well, using an SSB radio to actually test that later in the video. If I just go back to the main menu from SSB, we've got a modem test. If that's fitted, it'll go into that. That is available on the CMS54, but it says necessary option not fitted, because obviously you have to pay for these things to be fitted. This is a language select button, so you can select between different languages. It supports quite a few, including Italian there, and then back to GB for Great Britain. In the config menu, we can then go into configuring the instrument, everything from illumination to what time the display is on, the search routine, runtime, all sorts of different parameters in there, zoom, local oscillator, high or low, IEEE address for the GPIB port, four different types of printers that it supports, RF volt, meter range, and obviously impedances, key beep on and off, warning messages, and then you can do a master reset when you hit that button, and the instrument will calibrate itself once you've master reset. There's also another sub menu because we've got the little arrow up, and then there's further settings there where we can go into such as RF level, limits, AF level, squelch threshold, squelch delay, attack time, a measurement time for peaks and things. All that's quite important for measuring AM and SSB signals. And again, we've got further options on this side too. So if we go back to the main menu again, on this side we've got tones. So then we've got all the different cell call signaling standards that we normally find on most radio test instruments. Naturally, if we're going to put in CTSS tones, then that's done in the AF Gen mode within the RX test or TX test, where we can read the transmitter frequency of the CTCSS and also emulate the RX signal generator with CTCSS as well. But we've got all the signaling standards there, including I think they call it COCSS in ROHDE and SCHWARZ world. But not only does it do cell call and COCSS, which will be CTCSS, where you can enter frequency directly from a table instead of having to remember the frequency and manually type it in. That's all taken care of automatically. It does DTMF tones for telephone systems, all the usual cell call standards such as EA, EIA, ZVIE, CCIR, etc. And then you've got a fixed frequency generator as well. So you can select different modes. At the moment we're in mode 1, which is ZVEI, so 1 and 2. So you can go into all kinds of different modes within the test instrument, and then you can select what standard you want. So, you know, obviously if you press, I think it's 0, enter, then you can select fixed frequencies if you want. You could obviously go to DTMF, which is 10, enter, and then obviously you've got now your DTMF tones. And I think we'll have a look at this COCSS, which is 15, enter. Not available in this menu. All right, I've got to do something then. Oh, it's press 15, enter. Oh well, it's not available there then. So you can select all these different tones and things on there, which allow you to select all these frequencies and modulate that onto the carrier. So that's a little rundown of a tones system. Then we've got VOR, which is the VHF omnidirectional range locator beacon. And in there we can set all the parameters up, including the RF frequency, what the level is of the RF signal and the signal generator, the VRR, the carrier, the FM content, and then the different phases between the different locator signals, and then all that parameters set there, which we'll go into, and I'll do a full description of this, what we've got in the manual as to how that operates. So we'll do that later in the video, otherwise it gets too complicated. And again, instrument landing system ILS, locator beacon. Then again, we've got the very similar thing again, where we can set that parameter up too. So we'll look at that later with the Avionics options. And then we've got the impedance settings as well. So we can change all the impedance of the AF ports, which are these here, balanced and unbalanced. We can set up a termination for the AF ports, either 300 ohms or 150 ohms, whether it's a telephone handset that we're looking at for audio signals. Then we've got, again here, impedance measurement, AF1, different modes for the AF inputs and outputs, and then impedance match. So there's quite a bit to this instrument, there's quite a lot there. And then we've got the self-check. So when we press the self-check, then we can obviously do all the different routines, be it PAL calibration, distortion calibration, all the different cals we can go into there, and obviously a battery check if we're running it from an external battery, etc. So that's that. So quite a lot to it, and there's a lot more to come. For such a small instrument, it's quite complex in the way it operates as well, which you'll see in the next stage of the video. and we'll connect to radio up as well, and connect it up to the test set and start doing some test and measurements. So, with regards to technical information from the manual, we've got a pamphlet here from ROHDE and SCHWARZ with all the wherewithal of the instrument. Now, later on in the video, I'll show you these accessories actually working. We've got a remote control head, a VSWR bridge. We've got a remote antenna system, which forms a part of the front cover that covers a test instrument with the antenna on it. I'll show you that working as well, because we've got all these accessories with this instrument. Obviously, this little manual is a technical information manual for it. It's got a frequency range of 400 kHz to 1 GHz. This particular instrument is set up to do navigational VOR, which is VHF omnidirectional radio range, ILS, which is instrument landing system, marker beacon MB, and ADF Automatic Direction Finder, auto ILS or autopilot, and then homing. Communication, we've got basically HF, SSB, transceiver, VHF, UHF, AM and FM transceiver, cell call, selective call, and then there's intercom, which is a side tone test, and a crew station box test. So it's, you know, it's aimed at the avionics market as well. Technical information, I'll probably go and read this out towards the end of the video as like a closing piece, going through all the technical information as to you know, the features of the test set. So I'll read that out at the end. More technical information on this side, which is to do with the instrument and measurement capability and what the features of the measurements it can do, from SINAD to RF power, AF measurements, etc. And then we've got some breakdowns of the screens roughly, and now to set up ILS as well, instrument landing system. We've got specific measurement added value in the avionics fields, so there's all kinds of setups here for autopilot, etc. SSB testing, spectrum monitor, VSWR, obviously using that accessory I just spoke about. There's a carry case that comes with like a bag, so you can use it while it's in its bag. This antenna, which is quite clever actually, I'll show you this later. The antenna's carried in the case, and there's a lot of coaxial cable, and this is a metal box, so you can use it as a ground plane. And this is the antenna whip, goes up about 2 meters tall. This is the VSWR bridge, where we can measure antenna VSWR and mismatch, etc. Then we've got the automatic test procedures for what's available on the CMS for things like auto run testing and automatic measurement reports that can be printed out, so that if you're testing avionics systems, you can get a proof report. Then we've got things like test routines, programming and software management. Again, I've got this head as well, where you can connect this to the test set and run different programs and things from the actual instrument's GPIB port. Low cost of ownership, that's quite an interesting statement from ROHDE and SCHWARZ, based on past experience with component repair costs. So yeah, we could read about that. But then of course there's a technical information here, the specification of the instrument, and then finally I think more technical information. Again, quite a wide dynamic range on this instrument of various tests and things that it's capable of doing. The ILS stuff, aircraft navigational information, and then obviously general data and SSB things, and that's that. So we'll have a read at this later anyway, and go through that. The manuals are quite comprehensive with these instruments and well written, so we'll have a look at that. Okay, we'll get on with some tests. Right, so in TX mode now. We've got various modes with this. We've got frequency counter mode and set RF frequency. So for example, in set RF frequency, you could just type in the frequency if you know it, and then obviously it'll measure the frequency error here. So when you queue up the transmitter, it will tell you how far off the frequency is. Read the TX power, all sorts of things we can do with adjacent channel power as well. Now if I put it to frequency counter mode and keep up the transmitter, which I'm doing now, I'm measuring the RF power there. For some reason the frequency is not showing. Why is that then? I'll have to troubleshoot now to find out why that's not working. Let's have a look. Oh, there we go, look. Input 1 and 2. So if you select input 1, then it should work. Yes, there we go. So that's a little quirk there, you see, that you need to check that your RF input ports are selected correctly, because that was on input 2 for some reason, which is a BNC. And because of the way that the instrument measures RF power, there's basically a Schottky diode after the 20 dB pad, which sits behind this N-type that measures the RF power. So it directly rectifies the RF that's comes through the 20 dB pad that's in the RF attenuator section on the transmit monitor side to read the RF power. So even when you've got the second input connected for what is the frequency counter side of things, the RF power will still show, because it's still always permanently connected to this end connector here is the RF power meter, but the frequency counter runs off of actually measuring the signal after a predetermined level has been inputted into the frequency counter module for it to receive the frequency. And obviously with selecting input 2, the RF relay switched over to this, there wasn't enough signal entering the input 2, the isolation in the relay, for the frequency to read out. So that could lead you a merry dance. You could see the RF power, no frequency, and you might think your transmitter's dirty or there's a fault with your transmitter, and there actually isn't. It's just because you've left it on input 2, and obviously you need to flick it back to input 1, so thus the frequency will be read. I've been faffing about with this early, and it's remembered that I need to capture things like peak power as well, so peak hold, and obviously on that, if I go to the sub menu, yeah, we've got power hold, so get rid of that, and that should then allow the transmit power to go back to 0 when we're not transmitting. So it remembered what I've been messing about with earlier. That's the thing with the ROHDE and SCHWARZ. When you change any of the parameters or whatever, even on a power down and restart, it remembers what you've last done. So sometimes if you really mess it up and you can't quite remember what you've set it up to, parameters that are a domino effect on other parameters, it's sometimes best just to reset the instrument using the master reset, and that way you know you're not scratching your head. It'll default all parameters and then put you back to square one again. So now when I key up, because we've got input 1 selected for the RF input, it should read both the frequency and power, and then obviously the modulation content. So we'll flick that to D mod. We'll turn the volume up as well, so it should be able to hear ourselves. Radio test 1 2 1 2 1 2 3 4 5 5 4 3 2 1. Now select best range 1 2 3 4 5 5 4 3 2 1. Testing 1 2 1 2. So it's giving us the power, frequency, and obviously the modulation content that we're receiving on the transmit monitor. 5. So that was a modulation. Now I can put peak hold on now. 5 5 5 5 5. So now it'll tell us that it was 2.5 kilohertz plus or minus deviation. And likewise you can obviously hold the TX power as well if you want, so that's quite a nice feature on this instrument as well. Also we can set the frequency to 430 megs in this case, because that's what the transceiver's on, and that will tell us the frequency error as well. So it's giving us the error here, which is probably 250 hertz of frequency. So that will tell us that, and I think under that we've got duplex space, reference channel, LCH, or whatever, channel space and channel number. So you can put channel numbers in, you can channelize it if you want. Frequency, trans, whatever that is. So you can do quite a bit with it. Also you can inject an audio frequency into the transmitter by selecting the AF output, mod gen output, and then connect that into the mic input then on the radio, which also forms a test of a transmitter, so you're not having to talk into the microphone. You can set a particular AF level up at a frequency of 1 kHz, and then you can read the mod directly on there for accurate calibration of the transmitter deviation or modulation depth if it's an AM radio or an SSB radio. So that way automates it as opposed to having to scream into a microphone. So that's another thing that you can do. So what we'll do now, because we've looked at the RX and the TX side, we'll go to the what is the spectrum analyzer function. So we're now in the spectrum analyzer. Now on this particular test set, tracking generator isn't fitted. If it was, you'd be able to press track and then you could set up the tracking generator. If you want to see that working, look at my CMS34 video, because it's on there with the CMS34 radio tester. Likewise, a cable test isn't enabled on this one. They didn't pay for the option, whoever bought this test set originally. But that does distance to fault measurement. Again, if you want to see that working, have a look at the CMS54 video that I've done, because that option's enabled on that. So basically, in this mode, we've got the RF attenuator, auto, resolution filter, we've got RF level and RF offset, we've got input 1 and 2, so we've got high sensitivity capability where we can look at off-air signals as well, a look and listen function if you like on the spectrum analyzer from an antenna connected in here, or alternatively we can measure high powered signals coming in there, so that's where you'd select between input 1 and 2. We've got a center. We can either have a center frequency set up for the center frequency, or if we wish we can have a start and a stop if we're wanting to sweep a band. And then also we've got measurement facilities by pressing the freeze. We can then read the signal, its amplitude and other features as well, so we'll have a look at that now. So for example, I could set the center frequency to 4 3 oh, I made a mess of it already, clear. 430 megahertz. So that's the center frequency there. Now I'll key up on that. Obviously we've got quite a large amplitude there. So what we can do, I think it's on auto adjust at the moment. So let's have a look at this RF attenuator. And I think, let's have a look here. 20 dB RF attenuator. Reference level. Let's have a look, see if we can. Let's have a look here. It's a strange spectrum analyzer on this. Right, we'll set it to plus 49 dBm. There we are, look. And then we'll want the span setting up as well. That's something else we have to set up. Getting all kinds of weird things. Cable marker. Right, center frequency. Span. Oh, here we are, look, span. Right, we'll have that at 1 megahertz then. That's it. Right. Should get better resolution now. There we go. And how the spectrum analyzer works is it goes through all kinds of different sweeps to make up the signal there. So it works a little different to most other spectrum analyzers in that context. So let's have a look here. Let's set that at 2 megahertz then. Turn that bloody volume down because it gets on my wires. Let's have a look, see what we get now. Put a 2 megahertz span in. Span 1 megahertz. What am I doing wrong here? Must have messed something up, surely. Right, I found out where I was going wrong. Like an idiot, I'd not set the external attenuator up proper under RF Attenuator. I've set that to 50 dBs, and that was set too low, so its measurement was all off, simply because I'd well, basically what I'd done is I'd not set the input attenuator to the right level, so it was overloading the measurement. I'd alter the reference level, but not the actual auto antenna, the external antenna, the RF attenuator, should I say, level. So that's where I made a mistake, so that made the waveform all out of proportion. So to measure the waveform, we press freeze, and then now it'll put the mark, and it'll tell us that we're doing plus 44.5 dBm. And we can move the marker as well, up and down the carrier. What I've done here, I've selected a 2 megahertz bandwidth, and at the frequency of 430 megahertz, 50 dB attenuation on the RF input port, and then I've set the reference level up as well, so that we get the scale correctly. But that's what happens, you see, with some of these instruments. You've got to go through all these parameters to you know, to make it work properly, otherwise it'll not default it. Like on some radio test sets, it'll default to the maximum level, and then you have to reduce the level of the input attenuator or the bandwidth, so it gives you like a global snapshot. On the ROHDE and SCHWARZ it doesn't, it's quite specific, so you've got to go and enter the levels in manually, and then it will then show you the correct image on the screen. So naturally in this mode as well, we can select, I'm transmitting, if I go to quick, on there, I think that were it, quick, we've got the measurement of the frequency there. We can then change the span to, say, 500 kilohertz, and then now it'll measure the signal at 500 kilohertz as well. It's quite a good resolution bandwidth on this spectrum analyzer as well. The nice thing about it as well is that it's very detailed as a spectrum analyzer, and it's a very pure spectrum analyzer. It's quite high spec. Now we can enter in as well a start frequency, so I'll say 429 megahertz, and then a stop frequency of 431 megahertz, and then obviously we can look at any signals that might be within that frequency range. Likewise, if we're looking at an external antenna, we can read frequencies off air and do that as well. So if I transmit in, we can then look at harmonics further up the band if we want to increase that up to 1 gigahertz. So I can say, for example, the stop frequency now is 1,123,000 megahertz there, 130,000 megahertz. So we're starting at, put my start frequency in at say 100 megahertz. I think it's got perhaps a 50 meg. Might be able to look at 50 megs at a time, I'm not sure. So start frequency is say 425 megahertz. 475. I think, depending on what you previously set within the specs, it will denote its bandwidth at maximum that it can go to, which is connected with the resolution bandwidth. So that takes a little bit of working out, does that, because obviously the span, if we alter the span to 500 megahertz, then that might have it says too large, 50 megahertz. So I think it might only be able to measure chunks of the band in 50 megahertz increments. So if I set the span to 50 megahertz then, which it allows, 50 megahertz, 450, then stop. So if I set the start frequency to 400 megahertz, it only goes up to 450. So I can't select a frequency higher than 450 megahertz. So if I put 460 megahertz in, it'll then change the start frequency to 410. So it can only look at 50 megahertz at a time. But I'll check that anyway. But you can look at 50 megahertz anywhere between 400 kilohertz to 1 gigahertz. But I don't think it can see the full span, 400 kilohertz to 1 gigahertz. Only 50 meg snapshots at a time in it. But I'll look at that in the manual to see whether that can be changed. Because we've got the resolution filter 1 megahertz. If I key up again, that's 1 megahertz, 3 megahertz filter, 300 kilohertz, 1 megahertz. So yes, we've got offset, only possible with track gen, input 1, input 2, center start. So there's quite a bit to it. It's quite a good little spectrum analyzer. You know, you'd be surprised at what it can do. So yeah, that's a little rundown anyway of a spectrum analyzer. It works slightly differently to other spectrum analyzers in the sense that in order to measure the RF level, because it's just sweeping, doing a slow sweep at 50 megahertz there, you have to freeze the measurement, and then you get the markers then appear. It doesn't allow you to use the markers when the image isn't frozen. And then, as I say, as we looked at earlier, you're able to calculate 3 dB points from that. But it'll be a case of having to freeze the image. Now I've unkeyed the transmitter. It's not actually transmitting at the moment, but it's frozen the image there. So it'll only measure the RF level in amplitude when the image is frozen under freeze. Once you unfreeze it, it'll measure the level. So as long as you know what the graticule is, what the level is there, then you can see that at an instant. But if you want exact information, you have to freeze it. And then that's exactly what it does. It'll freeze the measurement now and then put the marker up, and then you can adjust the marker appropriately to read the level and frequency. So nice little spectrum analyzer. Right, we'll move on. Right, so now we're ready to make an SSB measurement. We've introduced an SSB equipped radio here that does upper sideband and lower sidebands on SSB modes, both on transmit and receive. We then have to get to the main menu screen by pressing the up arrow button there, whatever screen you were in before. That'll get to the system selection menu. We then select SSB mode, and then from there we need RX SSB because we're going to do the receive sideband test first. Now it's defaulted to CW at this stage, but if it was on any of the lower sideband, upper sideband modes, we will need to change that first of all to CW, because we need to align the SSB radio to beat the frequency to minimal beat between the receiver frequency carrier and the beat frequency oscillator in the radio. And we do that by adjusting the clarifier control there. All SSB radios have a clarifier, and the clarifier is used not for adjusting the transmitter frequency, but only for adjusting the receiver frequency. And those who listen to shortwave radio or HF radio, where they're constantly tuning into sideband modes, being upper sideband, lower sideband and double sideband modes, will know that when people speak on the radio, perhaps from the other side of the world, and you're listening to their transmission, sometimes they sound like Donald Duck, and more often than not that's the reason, because the clarifier needs adjusting. The clarifier finally adjusts the receiver frequency in the radio. It doesn't adjust the transmitter, it only adjusts the receiver. So if you're listening to somebody at the other side of the world, for example, and they sound a bit like Donald Duck, we would adjust this clarifier so that the syllable rate of their speech matches the normal rate in which you can hear. Otherwise they sound a bit like Donald Duck. So this is why we have a clarifier. The clarifier doesn't adjust the transmitter of the radio, only the receiver. And so everybody around the world talking to one another or listening to each other would always use their own clarifiers on their radios. Obviously there are differences between all radios because of the environment they're in, the model of radio that they're using, the type of equipment they were calibrated against. So many variable factors such as temperature all affects the frequency stability of radio. So that's why if I was transmitting on 27.5, my frequency might be just ever so slightly off in comparison to somebody who's also on the high channel who's I'm talking to, who may also be slightly above the frequency by a few hundred hertz. So therefore the listener would adjust the clarifier accordingly to pick out both conversations. Normally, if the radio is my radio's on frequency correctly and the other person at the other side of the world's radio's on frequency correctly, and somebody else many continents away can hear both of us on their receiver, they would clarify us in, and normally both our transmissions will be on frequency. But it is quite normal practice for listening to SSB radio transmissions where you have to adjust this clarifier. So how we do that in terms of testing on the radio is concerned, on the radio test set, and to check the alignment of the clarifier on the radio, is we first of all select CW mode on the test set. So we're generating a signal to the radio, but we're not modulating it. There's nothing on it, it's just a carrier wave, hence the term CW. Then what we do, we adjust the control on the radio, because this radio does all modes, AM, FM, upper sideband, lower sideband and CW. We go to our upper sideband mode and then we turn the volume up. And we can hear there's a constant tone there. So the idea is we adjust the clarifier so there's no longer a constant tone and we get a bit of a flutter sort of sound. That's what we do. And in doing that, what that does is it tunes the receiver to almost the same frequency as what the test set's producing. So as you can hear, it can go really high in frequency and down to almost nothing. Then we start going the other way, then we tune off. And what that is that we tune the receiver high at first, we've moved it higher, then we brought it back to centre and then gone lower. And so we need the clarifier to have very little beat frequency between what the test set's producing and what this is calibrated to. So we turn the volume up, and what we're listening for is this flutter. It's like, and you might see the signal meter do that as well. That means we're on frequency then, because the frequency of the radio is the same as the frequency of the test set. So we're starting to go up again. There. So now we've got no tone at all coming out of a test set, okay? Out of the radio. So that means we're on frequency. What that means is that when we do go onto upper sideband and generate a 1 kHz tone to modulate the transmission from the test set to the radio, then the audio frequency coming out of the radio will be precisely 1 kHz. Had that been incorrectly set, the clarifier, where we had a tone coming out, as we heard earlier, around about 1.5 kHz, for example, that will be added to the frequency of a tone coming out the test set, and then the two would sum together to produce, say, 2.5 kHz frequency offset. So therefore, if that was an audio transmission we were listening to, it will make somebody sound like the Bee Gees when they were singing. So this is the same thing here, Donald Duck syndrome, Bee Gees syndrome, as I like to call it. So you end up with a clarifier being in the wrong position, and that's how you would tune somebody in, so that you would get their syllable rate of speech to the normal rate of speech, because initially they sound all like Bee Gees, Donald Duck, that kind of thing. And so that's how we've aligned that. Now, generally speaking, the radio will be aligned so the central position of a knob indicates a centre frequency on the test set, and that means then that the clarifier is balanced between both sides. But as I say, all SSB radios have clarifiers, be them being marine radios for HF for ocean going ships and that kind of thing, or aeronautical avionic radios for communication across the big oceans, such as the Atlantic and Pacific Oceans. Aircraft using sidebands, military aircraft use sidebands as well, and military radio communications and international communications as well uses sidebands. So therefore the clarifier will be on all those radios. So now we'll go to upper sideband, and what we will do now, we will generate, I think if it's done correctly, level, I think we've got to set that to on. Let's have a look, see what I'm doing here. Right. And then level. Level 2. Is that 300? I think that needs to be 1 kilohertz, doesn't it? 1 kilohertz. There we are. Level. Oh, is it AF1? Maybe that's got to be 1 kilohertz. Oh, there we are. Does that when you know what you're doing, doesn't it? Right, we'll turn that one, that level 2 to off. Right. 1 kilohertz. So now we've got a 1 kilohertz tone coming out. If I was to adjust that clarifier, then we can adjust the frequency. So that's how we would tune somebody in. So that's like an example of tuning in a sideband transmission. So if that was replaced by speech, that 1 kilohertz tone, then that would mean that somebody would be intelligible, you'll be able to understand what they were saying. Whereas if a clarifier's like that, they sound like the Bee Gees or Donald Duck. So that's how we adjust the BFO on the radio, the B frequency oscillator, clarifier, etc. So we'll go to lower sideband now and do the same there. So now we need to set the radio to LSB, and now we're on lower sideband, and of course we're monitoring the same. Now if I go to set RF frequency and we adjust, see this is 1 hertz, 2 hertz, whatever, 3, 4, you can see as we adjust the frequency of the transmission to the radio, then it would have an impact on the modulation frequency that's received. And so that is a demonstration really of the product. The modulation is demodulated, and only possible to be demodulated on an SSB radio if there's what's called a beat frequency oscillator. Without the BFO in the radio receiver, it would not be possible to listen to a sideband transmission. Indeed, if you're on AM on an ordinary radio receiver or scanner or an AM radio receiver, and somebody's transmitting on that frequency in sidebands, all they'll hear is it's like it's like that. You just hear this and that's all you can hear. You can't hear any speech. You can tell something's there, but you can't hear it. It's just unintelligible, and that's because you've not got the beat frequency oscillator. Without the BFO, you've nothing to beat against that carrier, and so it's a product really of the carrier mixing with an oscillator that's in the radio, and the two collide, and the beat frequency oscillator, the radio, and the modulation content of the sidebands have to beat together. So you've got a constant frequency of a beat frequency oscillator where it's beating against the exact frequency of the radio receiver signal that you wanted to demodulate, and then you've got the sidebands, which is a combination of amplitude modulation signal on a sideband. So it's not on the center frequency, it's upper or lower sideband, and the difference between the two, the beat frequency oscillator of the radio and the radio signal you're listening to, the difference in frequency between them as they're being modulated would mean the difference is the audio content that you're wishing to receive. And that's how sidebands work. So we have upper sideband, lower sideband, and indeed some of the radio modes are double sideband, where we can have two sidebands together, double sideband. You can have, like we talked about previously in telephone transmission, what was on the old microwave radio networks many years ago, in the heyday of microwave transmission, we used sidebands on the multiplexers on microwave radios, so you would have many sidebands all in the RF carrier on the microwave link from point A to point B, and you could transmit thousands of phone calls down that one microwave link, because each phone conversation would be on one sideband, and then you could multiplex each sideband as well, so you could interleave even more phone calls on it, and these were called muxes or tribs, and so you would have lots of sidebands being broadcast all at the same time. So there's a lot of interesting things around sidebands. In terms of radio propagation, sidebands is immense. It's actually enormous, the distances that can be achieved worldwide, obviously, distances. So the types of things that use sidebands in the world, as we've already talked about, mainly the marine, aeronautical, military, but also there's lots of other things like ham radio, obviously. We have navigational beacons and aids, and search and rescue aids and beacons. These rafts, life rafts that have beacons on them, work on sidebands, on international con distress frequencies. Search and rescue beacons, SABs, all kinds of things work on sidebands. Foreign and Commonwealth office embassies and spies and clandestine communications, a lot of it's on sidebands. Radio teletype and news gathering agencies around the world use sidebands. Long distance education and communication across countries that don't have the internet and are very desolate or don't have wide usage of electricity, or telecoms networks like ground-based networks, cellular networks. There's still lots of places in the world where there's no landline communication or internet like we are in the Western world. We take it for granted, and cellular networks, and indeed there are some parts of the world, particularly mountainous terrain, where it's not possible to use a sat phone either, satellite phone, because the peaks of the mountains adjacent to where you're working from or living blocks the signal from the sky, depending on what the satellite constellation is. So there's all kinds of uses for sidebands, and the fact that it uses ground wave as well, and ionospheric ducting in the atmosphere, and stratospherical ducting, ionospherical ducting, F1E1 layers, all these different layers in the atmosphere, and we can bounce a signal off the ground. At one point in the planet we can transmit a signal on sidebands on HF. It can hit the Earth's atmosphere, duct through the Earth's atmosphere, come out halfway around the world, bounce off the ground again, or ocean, hit the Earth's atmosphere and go around the other side of the world, and thus we can get international propagation, which means then the bands open up and we can communicate around the world. And there's so much involved with the Aurora Borealis, the particles that are coming in from the sun into the north and south poles of the Earth, that then have an influence on the Earth's atmosphere, how it propagates radio waves, and that's why we have beacons across the HF bands, so we can listen to them to see how good the propagation is in the Earth's atmosphere. And these beacons are transmitted from all over the world, and so therefore as an SSB HF user you can listen to these beacons to find out which beacons you can pick up and which beacons you can't. And it means then the ones you can pick up, those bands tend to be more open, and perhaps you can take advantage of the Earth's atmosphere to get your signal around the world. Indeed, I used to know somebody who was one of the RF engineers that worked on the Antarctic expeditions into Antarctica and the North Pole as well, both the South and North Pole, and they use HF radio for that purpose as well, so they can communicate internationally and communicate with family. People that use these yachting things internationally, they have SSB radios, a backup for if a sat phone doesn't work, and these round the world ship type racers and things, yacht racers, they use SSB as well. There's used all over the world still, it's very, very world possible with regard to radio communications. So we'll go back to the transmit TX SSB. We'll just go to upper sideband. We'll go to mode USB. I do want to listen to what's coming out, so I need to go to mode, I think it was, how was it now, decode, is it that? I think it was, no, it's not that. I wanted to be able to listen to it. I can't remember how I did it. Filter, distortion, input 1, 2, power decode, scope mod. Oh, there we are. Is that it? I think it is. There we go, look. And you can go D-mod. So you can have mod external, AF, D-mod, or distortion. So it's on D-mod anyway. So I want to be able to listen to it, you see, with the volume control up. We might have to faff about with the scope in order to get the best range. Now, we might want the mode, depending on the power, we might want to go with, I'll leave it to auto, because it's the test's got to catch the RF carrier in order to then demodulate it. Ideally with SSB transmissions, rather than just talking into the microphone like we're going to do now, you're best off having it so that there's a signal going in from the AF output of the mod gen output socket into the mic, and you generate a constant tone. That way the test set can pick that up better, it can measure it better, and also then you can check that the radio won't overmodulate at certain AF levels as part of the service manual specification on the radio. So anyway, we'll see what we pick up. Radio test 1 2 3 4 5 5 4 3 2 1 1 2 1 2 5 1 2 3 4 5 5 4 3 2 1 1 2 1 2. So that's what we're picking up, you see. I think the amp, I'm not sure what that is, amplitude, there we go. 5 1 2 3 4 5 1 2 3 4 5 5 4 3 2 1 1 2 1 2. So that you can hear it coming out, you know it's working. You can then beat a frequency with it if you want as well. There's all sorts of things. You can also hold the power as well, like we've got it set there, so it tells you it's doing 16.3 watts maximum in the envelope, because obviously the RF carrier is going up and down in amplitude modulation as part of a sideband, and that's where you get the harmonic energy in the transmission in order then to be broadcast around the world. It's very difficult to explain, but if we're on FM on that same frequency, we will get only a partial the distance that we would do on sidebands on the same frequency, and it's down to basically the punch that the transmitter has with the RF carrier, and the fact that SSB signals propagate much further than AM or FM modulated carrier waves do. And it's down purely to the punch that the transmitter's got, the energy in the carrier, and the fact that it's capable of propagating. Then once it's thrown out into this atmosphere, it can then propagate in that mode, and it's more to do with the mode of transmission as opposed to the RF power and the frequency. And that's why SSBs are so useful, SSB radios, international communications. So that explores the peak power measurement there. We can remove that, and then you can measure power in real time. There's also the peak envelope power measurement as well, where you can measure that. 1 2 3 4 5 5 5. So that'll measure that. Obviously we've got power hold and then power hold reset as well. Let's have a look. So there's all sorts of little things that you can do, you know. If a radio's got cell call on it or whatever, then got all kinds of gates here as well, mode, period and gate, so you can trigger it. There's a filter you can have as well. There's all sorts of natty little things that you can do with it. One of the other things as well that I'd like to show you that I found out is, if you, at the moment we've got the oscilloscope here, if you go to the config screen as well, and this is in all modes by the way, not just in SSB, go to the config screen, you got a thing here called zoom. If you press that and then go back to where you were before, and then in our case ARX SSB, you then get the bar charts, and I'm not sure if it'll display the scope bigger, but I haven't seen that, but it just basically displays the bar charts. So that's quite interesting, and same under TX test as well, so that's very interesting. So you can do quite a bit with it really, and although I think when you then press the down arrow, let's see what it does on SSB. So if I go back to SSB tests, so on upper sideband we're on USB there. 1 2 3 4 5 5 4 3 2 1 1 2 5 1 2 1 2 1 2. So if I turn that down, so you got your power moving up and down, and then distortion as well. That's if you were feeding a 1 kHz tone into the test set. So it is quite a good little test set. Okay, we've taken all the lids off the instrument now and we're ready to have a look inside. Obviously the first thing that we can see here on the internals is a power supply section on the rear. It's not normal that these fail in in quite the same fashion as perhaps on other radio test instruments where there's common power supply failures on many radio testers that I come across. But the ROHDE & SCHWARZ test instruments, the power supplies are very reliable, I've found. Don't get many problems with them at all, if at all ever. So good power supplies in these. This card here is the audio interface card as well. That deals with, you know, the audio control interface for the front sockets, for the AF Gen, and for other options as well that might be fitted, like the ILS, VOR options and things. These sometimes on these cards. This unit here is the RF output stage. So this is where the SIG-Gen is located in this module. So this generates the receiver signal generator output, RF output. Amplifiers are in there as well, which then lead off to this attenuator module, which we're going to speak about next. Now, obviously, when we're making a transmit measurement into this test set, there'll be a frequency counter, a modulation analyzer, and the capability to use the spectrum analyzer is also in these modules, which are detailed. But basically the transmit monitor side of things is dealt with through the, first of all, attenuating the RF signal in this module here, and that's what this is. This goes the full depth of a test set, does that module. Now, on the CMS33 radio test set that I did a repair video of, and no doubt it's the same in this, because it looks the same module, there's a specially designed ROHDE & SCHWARZ pi attenuator RF resistor in there. It's about 26 dB. It's actually got two parts to it. It's got a 10 dB attenuator etched onto the same ceramic tile, as well as a 20, is it? No, a 16 dB attenuator etched onto the same tile. And they're both switched in and out with a relay, so it can either be 26 dBs totally, or just 16 dBs. So the RF power comes in from the front socket, the N-type, which is on the front here. It goes to this module. And on the CMS33 radio test set, it's a common fault, probably the same on the other CMS ranges of test set, where the ceramic tile that's got it's like a glass tile, it's made of some kind of an oxide, but it's like glass basically. It's bonded to a copper base, and then the etch onto it, the resistor elements. Basically that tile cracks, and when it cracks then it breaks the electrical connection through the RF attenuator resistor section, and then it doesn't read RF power, it doesn't work properly. So there's two halves to that resistor. There's one half which is when it's in duplex mode, which attenuates the transmit power down so that the receiver SIG-Gen output can be fed into it in one direction, whereas the transmit power is obviously read by a Schottky diode on the board, which is read off by some of these wires down here, which go to op-amp circuits. The temperature compensation diode as well. And then on top of that, then the output of that terminating resistor is then fed into what is the receiver section after the RF power's been dissipated. And that's so in duplex mode you can get an RF gen signal going out at the same time as monitoring transmit signal coming in, without the transmit signal damaging the RF attenuators, which are small surface mount resistors mounted in several sections in that module, which also houses within it step attenuator relays which switch in and out depending on what the RF level is that you set for the output. Now obviously the transmit power coming in at the same time as the receive signal going out, the transmit power has to be reduced to such a level after it's been measured that it doesn't then interfere with the receive signal generator's output. So that's why you have the two attenuators, so that low RF levels can be measured with only 16 dBs of attenuation, but when the RF level in watts gets above a certain level, then it'll switch in a second RF attenuator pad, which is mounted again on this ceramic tile, which then is an extra 10 dB, making a total of 26 dBs of attenuation before it gets to the receiver front end section, if you like. So Basically it's to prevent the transmit signal from colliding with the received SIGGEN signal coming out and then causing damage to the step attenuator. As I say, on the CMS34 series, that part that's in there which does that, which is only a part about that big square, bolted to this heatsink that you can see. There's a fin, these fins here that keep it cool. They crack, and obviously they're very costly to replace, about £700. So, you know, it makes it very difficult to afford that if you've bought a test instrument second hand. Now, on this particular test set, because it can stand 150 watts, what they've done to try and circumvent major problems with that resistor, on this particular model of test set, they've introduced what appears to be, I think it's a 6 dB attenuator, which is this here. So this module is connected via, what is, if I just turn it round a second, so this is the N-type on the front there, front socket. We've got this solid pipe, rigid coax, that goes up this to that module, which is just here. And this is bolted to a heat sink, which is bolted then obviously to the chassis rail of the test set, which is all metal anyway, no plastic on this, so it wicks away the heat. So the 125 watts, whatever power it takes, goes up the chute, up there to this 6 dB attenuator, I think it is. It attenuates the signal by 6 dBs, which reduces it. For every 3 dBs, well, half the power. So it's like 3 dBs, say 100 watts coming in, will be then reduced to 50 watts. Another 3 dBs then will reduce 50 by half again, which will be 25 watts. So with 100 watts coming in, you're going to get 25 watts coming out there, which then goes into this load resistor that we just talked about, that's mounted in here, the pi attenuator, which is a little ceramic tile that I was telling you about that cracks on most of these radio test sets. So that's a little breakdown of that. Of course, the output power from the signal generator module, which is here, has also got to be take in mind these attenuations as well, so that it overcomes the attenuation within the RF attenuator section for the transmit side, so that when it's in duplex mode, then basically it can send a signal out at the same time as receiving a high powered signal coming in from a transmitter, because at some point the two collide. But when they do that in this module, the TX power is attenuated to such a low level anyway, milliwatts, that basically when it does collide with the received SIGGEN output, it doesn't then damage the step attenuator in there or the SIGGEN RF amplifier output stage, because obviously we're only dealing in millivolts to microvolt level in that case. So that's that. Now on the CMS54, 52 and CMS50 series radio test sets, because the RF output power on input power on the N-type is only around 50 watts, they don't have that extra attenuation built in using this RF attenuator here. So the pipe from the N-type comes directly in to this connector there, and then the output of that 26 dB attenuator then connected off then to the module that deals with the transmit sampling for demodulating, well, basically the frequency counter, demodulating the TX mod, spectrum analyzer. The TX monitor output's fed out that 26 dB attenuator, and then the receive signal generator input is basically this bit here. So that's a SIGGEN output at a predetermined fixed level that's going in there, and the relays in here are controlled by this PCB, which switch them in and out. This module has a high output level, obviously, because it's got to compensate for all these attenuations that are going off. But in between that stepped ramped attenuation, each time we go through the ranges, as we adjust this rotary control on the front, and we're turning the level up and down, Within the signal generator module itself, what is the output stage, which is this module here at the back, this one. There's a pin diode attenuator section in there, so as you adjust through the range, before it reaches the next 10 dB, 20 dB, whatever step, where the relay would click in order to get those finer adjustments, there's actually a pin diode attenuator, and that adjusts just that 10 dB range or thereabouts very finely as per a DAC, a digital to analog conversion process, which controls the voltage to the pin diode and thus attenuates the RF output very finely until it gets to the next stage where it goes click and puts in another relay then to step up the RF. So you get those fine adjustments between the major steps that's achieved through pin diode attenuation. This module here is a synthesizer. So this generates the frequency that's used for tracking the TX monitor side for the frequency counter, where it can auto track the signal coming in. It also generates basically the voltage controlled oscillator phase lock loop for the receive signal generator, and as part of the spectrum analyzer it allows a signal to track as well when it does its sweeps. So that's those two modules. And obviously between these two there'll be the frequency counter for the TX monitor, etc., as we just discussed, as well for the TX side, and not just for looking in on the frequency as well, but also reading the frequency once it's been caught, and then demodulation as well. Now this particular module here, this one is I'm just looking at some information I've got. This is a measuring section, is this module. So this is also to do with the frequency counter, spectrum analyzer, TX modulation, as well as synad and all the other bits that the instrument measures is done within this module. The majority of the tasks that it undertakes, part of these measurements, is all done in here. And then this module at the very front here is the digital board. So that's where the microprocessor or the intelligence of Avionics, all based on that. All the digital functions of memory, the calibration settings, everything's all held here. And then the LCD drive and the keyboard reader multiplexer have got outputs here, one for the LCD display and then for the keyboard. We've also got a power supply, an audio cable coming in here as well. I think it's mainly audio, that, believe it or not. I think the power supply goes through the board on the bottom. You'll notice as well there's two blank slots here. Now on the CMS34 test set that I've got that's fully featured, it's got all the options added to it. These two are populated. One of the modules that sits in here is for the signal tracking generator for the spectrum analyzer. So it does distance to fault measurement on coaxial cables, as well as a RF tracking generator for measuring filters and things like that you do externally. So that would sit there as a tracking gen option. The other module that would go here, that is for, if I can think about this just for a second, duplex. That's it. That was on the tip of my tongue and I couldn't remember it. The duplex test. So that is basically again another synthesizer and RF monitor, if you like, that sits in this module that then allows both the transmit and receive measurements to be taking place simultaneously. So if a duplex option is fitted, we would have a module there. If a spectrum analyzer tracking gen option's fitted, that will be fitted there too. So that's a little rundown of that. Now underneath, obviously on the front rather, before we go to the underneath, this is all die-cast metal, etc. But behind here you've got the LCD and keyboard section, which we can't quite see, but it's basically in this section here. As you can see as well, before we turn it around, look underneath, all the adjustment points are all labelled as well, which is quite nice. So if you've got the extender card and you've got the module sat outside here, so you can get to all the adjustment points, it's quite easy to do alignments and maintenance. There's some adjustments through the top, but not many. Majority of them are through the actual modules themselves, which is accessible if you've got the card risers. If you don't have the card risers, you could take the covers off, solder cables onto the PCB directly, and then make your measurements while it's in situ. There is enough space between the modules to get most coaxial cables from taking measurements down there. Well, it's not ideal, but sometimes you have to just deal with what you've got. So looking at the underside now, common architecture again on ROHDE SCHWARZ test instruments. To release the modules within the unit, you have to basically slappen these screws off, and these metal rails slide. They're like locked back. To unlock then the modules that are sat in, they're sort of captive with this rail. And so to remove a module after you've unplugged all the cables and everything, obviously, then you click this back, these two rails, and then it frees up the modules to come out. So that's how you get them out. Common architecture with the motherboard in the middle. You'll see that on nearly every ROHDE SCHWARZ test instrument. They're always got that kind of common design. And then you've got your ribbon cables and everything that feed power rails to all the modules, again making it easy to measure those voltages. The cables themselves are all numbered, so if you unplug them, as long as you remember what numbers went where, if you've not got the service manual. If you have got the service manual, it'll detail the numbers of these cables for making measurements while you're doing repairs and diagnostics. But all in all, very well built, very well constructed, no plastic or anything like that. It's all good solid metal. This looks plastic, but it isn't. It's actually all solid metal. The front's metal. Okay, we're joined by the technical manager, who's decided to make an appearance. He just reminded me that I need to tell my viewers all about this module, which is the RF Attenuator section. And he said I mustn't forget to tell everybody about my experience with the CMS33 Radio test set and ROHDE SCHWARZ customer service, and the architecture of that module and why it's so different to most other test sets. So here goes. Well, obviously on this particular test set, because it deals with such high powers in comparison to some of the other CMS series of radio test sets, we've got a first stage attenuator before it arrives into this module. And basically the top bottom of it is that this module does actually soften the blow, if you like, for the main RF attenuator that sits here in this module. Now the thing is with it is that naturally in the other test sets all the RF power gets dumped into this module, and it obviously causes thermal heating of the RF substrate resistor which is in there, which is specially designed by ROHDE SCHWARZ. You won't find that kind of resistor in other radio test sets. Now I'll show you the type of RF attenuator resistor that you'll find in Marconi, Agilent, Advantest and Ritsu, Aeroflex test sets in a moment. But the issue that you get with these test sets, with all of the radio test instruments that ROHDE SCHWARZ produce, all the spectrum analyzers, all the instrumentation basically, is getting all the spare parts. That's the main challenge. And it's very, very costly as well, and that's what often makes these test sets unviable to repair, simply because the repair methodology that ROHDE SCHWARZ sets out is that the component parts are actually so expensive that often people opt to replace the modules directly. And indeed, in my case, the CMS33 Radio test set video, which is on this channel if you want to have a look at it, does detail the repair that we did on one of these modules. And unfortunately in that case I had to deal with ROHDE SCHWARZ UK. Well, I didn't have a very good customer experience with them, I'm afraid, and they were very, very non-supportive. They priced the part at £700 just for a terminating resistor inside the RF module. So obviously I didn't go ahead with a repair on that, and I still save that test set to this day for future parts availability and to try and get it going at some point in the future. So it's in the awaiting inspiration shelf at the moment. But basically much to my amazement, there's a common failure with these modules, and that is the resistor for the RF attenuator for the transmit power absorption cracking, and it physically cracks, and it's well known by ROHDE and SCHWARZ that it physically cracks. And the issue there, of course, is that when a customer presents such an issue to ROHDE and SCHWARZ, I would have thought it would be in their best interest to at least look after the customer insofar as offering a replacement part at a reasonable price, which £700 for a resistor is not a reasonable price. And secondly, knowing the fact that it's a common failure on these test instruments, even the ones that were still in warranty, I've read from German articles, still had failures with the resistor cracking. And this has obviously progressed on to 20 years later or thereabouts, depending on the production age of the test instrument, where that's still occurring. So it's very, very difficult for me as a repairer to justify spending £700 on one singular resistor. And I'm sure most people with a reasonable mindset would agree. Now, what I'm surprised about, which is certainly not the case with other manufacturers such as Agilent, Anritsu, Marconi, when they were about, and Aeroflex, when there was a production failure, there would be a recall, and they would often acknowledge that, well, they would offer the customer the chance to return that module to them, and they would then do a repair exchange, perhaps on a better price package, because obviously it was down to a component failure they're making. Or alternatively, they would offer that part at a significant discount, or they would offer to repair it free of charge, even after it dropped out of warranty in some extent. And I've certainly had that happen with other instruments in the past, because the companies that I've dealt with in the past have got good customer service in mind. However, ROHDE and SCHWARZ UK, I can't speak for ROHDE and SCHWARZ Germany, because they don't allow you to deal with them directly when you're outside of Germany. You have to deal with your countries that you're in representative of ROHDE and SCHWARZ. So in my case here in England, it was ROHDE and SCHWARZ UK who I dealt with, and they were very, very poor to deal with. And when you compare their customer service against other companies that I've approached in the past and recently for customer service, their customer service was exceptionally bad. And the negativity that you get from ROHDE and SCHWARZ with just basic price inquiries is unbelievable. I had to chase them up, I had to pursue them, argue with them, just to try and get, repeat the quotation request several times, because I'd lost all my details. Even though I'd set it up on their own web portal, they couldn't get the quote to me properly, even though I got an account with them and a web portal username, password and everything all set up where you're meant to receive your quotes. And then I had to have an email from the person at ROHDE and SCHWARZ UK who then acknowledged that the portal didn't work for them, and they had to then separately email me with the quote, which they did ultimately, with a shocking price of £700. So yeah, not very good customer service from ROHDE and SCHWARZ really. The fact that they didn't acknowledge that it's a common fault, it's a known production fault with them, the fact that they weren't interested in helping me, the fact that they couldn't even organise themselves in such a fashion where they could even professionally give me a quote without making a mess of it, and me having to keep chasing them, which a customer shouldn't have to do that. And then the fact that the price was, lottery numbers, it's just impossible really to deal with companies like that. And it's such a shame really, because that's now set a negative precedent in my experience with ROHDE and SCHWARZ. But most test instruments use a completely different methodology for attenuating RF signals when it comes to transmit power. Now, for some reason, ROHDE and SCHWARZ decided they wanted to reinvent the wheel, and they like inventing their own bespoke designs and their own componentry and manufacture their own processes basically in designing these components that are in these test instruments, particularly the RF side of things. Now, I've got with me here an example of a type of resistor that you'll find in most radio communication test instruments. What would be in a module similar to this here, which is no doubt what's in there actually. But knowing Rohde and Schwarz would probably even design that differently as well. But basically, I saved these from various bits and bobs, but you basically get attenuators like that, manufactured by companies such as KDI that used to belong to Aeroflex, I think, or these other companies that build them. And these are basically RF attenuator pads. And you'll find these in Marconi instruments, HP Agilent radio test sets, Anritsu Advantest, every other manufacturer on the planet, apart from Rohde and Schwarz. And these resistors can stand many hundreds of watts. They're very reliable, they're very good, but if you're stupid enough to blow them, at least you can buy a replacement part. And you can get these quite cheaply from most suppliers, including Element 14, RS, Farnell, you name it, AliExpress even, Amazon, eBay. They're sold everywhere and they're cheap. Even directly from the manufacturer, like this KDI one here. Although it's only small, this can take about 100 watts. That KDI one there, pad, that can retail at round about £40–50 upwards to 100 maybe, but certainly no more than that. You can often get them less than that, £10–15, you know. So this is what you have, you see. You have these basic components in other radio test sets, and they work perfectly well. The technical manager's getting bored, so he's going to have a nap now, but they work perfectly well with the radio test sets that other manufacturers make, and they are cheap to acquire and they're readily available, and they're not a specialist component that is only made by one manufacturer. So these have a higher power handling rating than anything that Rohde and Schwarz has produced so far within these instruments. They also have a much wider frequency response and frequency operation range than the Rohde and Schwarz product does. So I don't understand why they don't use things like this, because every other manufacturer does. But Rohde and Schwarz have to reinvent the wheel. And it's cost them in this case, because there's quite a few problems with these attenuator resistors cracking. So the design isn't quite up to it. Hence the reason why they're obviously using this kind of attenuator first to drop the power before it enters this module. So they've obviously not been able to manufacture a higher powered version than that on its own to do away with that. So this is the issue. You got £20 versus £700, you see. So obviously, from my point of view, when you're looking at Marconi instrument, HP Agilent that uses components like this, it's more easy for a repairer to be able to acquire components like that. And this is the point I'm trying to make, Rohde and Schwarz. It's a bit like, you know, you're buying a Ferrari. You're not going to be able to pick the parts up from anywhere. You might have to go direct back to Ferrari. And so even after all these years, Rohde and Schwarz have still got the monopoly on these instruments insofar as spare parts are concerned. And the pricing regime is, I would say, extortionate. I would go as far as saying that. And I would happily argue that case with any Rohde and Schwarz representative if they were to reveal themselves to me. I would definitely have a very one-sided conversation with Rohde and Schwarz about that. But this is a type of thing that you're going to come across with all Rohde and Schwarz instruments, whether it's an RF resistor, an LCD display, a specialist component. You're going to have this issue where you're either tied to Rohde and Schwarz or you're going to have to scrap the test set. So that's what I wanted to tell you about there. So buyer beware. When it comes to Rohde and Schwarz instruments, if you're going to purchase a Rohde and Schwarz test instrument, make sure it works 100% before you take it. If you're buying it second hand, make sure you test it thoroughly using another instrument to give a reference source, to measure transmit power, receive signal generator. Don't part with your money until you know that it's 100% working. There are problems with these test sets with the LCD displays failing and backlight issues. There are other issues that we've just spoken about with the RF attenuator section. Some of the modules are incredibly difficult to get hold of as a spare part to just swap out, just to check that it's not another module that's failed, but you know, just to exclude that module from being a possible source of failure. Very difficult to get spare parts on the second-hand market, and really, you know, you're beholden to ROHDE & SCHWARZ themselves to supply the components if you want to get one of these working. I think it's a negative trait that ROHDE & SCHWARZ prevail, particularly ROHDE & SCHWARZ UK, when, you know, you can't acquire basic component parts at a reasonable price. I've been doing repairs for a long time with radio communication instruments and radio communication products, and test and measurements, and it's not often that you pay that kind of money for an RF resistor. Let's put it that way. You'd expect to pay that for a module or a subcomponent, a sub-assembly of a module, or something quite major, like an LCD display or a cabinet front or something like that. But you wouldn't pay £700 for a resistor. That'd be like somebody saying to you, I want £700 for a fuse in a plug. You go, you know, you're joking, you know. So this is it. It might be a specially designed component, but it's no different from using the resistors that I've just shown you. And again, I think it's ROHDE & SCHWARZ just trying it on, personally. I don't know. It seems like ROHDE & SCHWARZ UK might be a bit dodgy, in my mind, for trying to quote such a price. But anyway, that's my rant on that. And I think it's justified based on the experience that I've had. It's a shame that the experience isn't more positive with ROHDE & SCHWARZ. And you will see on this channel the repairs that we've done on ROHDE & SCHWARZ instruments, just how difficult it is to get parts. So, you know, if you're a small customer, if you're somebody who's purchased one for your business, or you're wishing to use it in your own workshop, be aware that at some point in the future, if it goes faulty, you will face quite a considerable repair bill when it comes to getting spare parts. Okay, so we'll have a read at some technical information about the product, and just look at its features and specification. Obviously, as part of this product line, it's got navigational aids for VOR VHF omnidirectional radio range, ILS instrument landing system, NB marker beacon. It's got ADF Automatic Direction Finder, and then it says auto ILS, automatic ILS equals autopilot, and homing function. For communication, we've got HF and SSB transceivers, VHF, UHF, AM and FM transceivers, and cell call, selective call. There's an intercom test, a side tone test, and a cruise station box test for Avionics in that kind of a configuration. Okay, so we'll have a look at the information. It says the CMS33 is a complete test set for testing the communication and navigation instruments in aircraft, both with a direct connection to the antenna input of the transceiver and off-air using a test antenna. Comprehensive measuring equipment including VSWR, spectrum monitor and transient recorder opens all kinds of measurement applications. Off-air tasks for fast and comfortable testing of the navigational instruments without connecting and exchanging hard-to-get-to antenna inputs. The only radio tester with an integrated VOR ILS generator, which has already been established on the market and well tested by national aviation control authorities and armed forces. Ease of operation thanks to clear operational concept and a large 9-inch LCD display. Interaction with the operators are reduced to a minimum by means of test routines consisting of clear, user-specific instructions. This means that even complex measurement tasks in large service organisations can be standardised and reproduced. Prepared automatic test routines for fast verification of entire nav-com-intercom equipment. Automatic or manual impedance matching to intercom networks ensures no operator error and a complete one-box solution. Minimal weight and small size for portable and stationary use, can be comfortably used even in very confined spaces such as cockpit, due to an optional small external operating panel. Minimum power consumption ensures long battery service for life on-site work. Modular feature-orientated concept with self-test and automatic self-adjustment to permit long calibration intervals and low operating costs. Simple and safe logistics for programs and their modifications. Now, as for the technical information, it says, on the basis of more than 20 years of experience and the development and manufacture of compact radio testers, the Radio Communication Service Monitor CMS33 is a consequent development of successful CMS family for the demanding applications in the avionics field. A universal, most modern concept, minimal weight, small size, and the most simple operation render the CMS33 equally ideal for mobile use on site as a ramp tester and, thanks to its outstanding data and flexibility, as a bench tester for repair and maintenance in laboratories. The CMS33 has been developed to match the special requirements in the measurement of communication and navigation instruments. Short test times, low operating costs, simple operation, and the CMS33 being one-man portable were highly important design goals. Portability, splash protection, universal power supply, off-air measurements using a test antenna, and a remote operating feature for direct use in confined places additionally improve usability. All further accessories such as VSWR, insertion unit, cable, program card and user guide can be accommodated ready to hand in the transit case. The CMS33 tests AM, FM and SSB transceivers in the HF, VHF and UHF range, including the necessary selective call methods, cell call, and also permits the audio analytics of the intercom network. This satisfies the test requirement in the field of aircraft communication. For the navigational test, the CMS33 generates exact signals for a precise reading of a navigation instruments. All necessary signal sources to test VOR, ILS, marker beacon, autopilot, homing and ADF are available. In automatic operation, a pass-fail message indicates conformity or non-conformity with settled tolerances in order to ensure a fast exchange of a defect unit. Program cards store the exact measurement results which, when printed out, serve as an important source of information for repair. Ultimate precision makes the CMS33 the ideal measurement equipment also in repair workshops. So under measurements, the CMS33 offers a complete measurement program of a modern radio test set. It talks about the CMS family as a wider portfolio as well. It goes on to say, thus the CMS33 replaces various measurement instruments in the workshop. Further, it provides additional measurement equipment for the efficient and effective operation of transceivers and navigational receivers in aircrafts. General test of measurements: RF synthesizer from 400 kHz to 1 GHz, resolution in 10 Hz steps, with AM, FM, pulse modulation and multi-tone modulation capabilities. 2 independent modulation generators, 20 Hz to 20 kHz each, resolution of 0.1 Hz, a cell call coder, and various other selective call standards, VOR and ILS signal generator. Measuring facilities is RF frequency counter, RF frequency offset counter, RF power meter from 5 mW to 125 watts, selective RF power meter down to -100 dBm, modulation meter for AM, FM and phase modulation, weighting, plus peak, minus peak, peak hold, plus or minus peak, -2, RMS and RMS squared. AF voltmeter with peak and true RMS weighting, synad and distortion meter with variable test frequency, signal to noise meter, AF frequency counter, selective call decoder for all standards, an oscilloscope, transient recorder, optional. Filters, the CCI-TT filter for weighting of relevant standards, continuously tunable bandpass filter from 50 Hz to 5 kHz with high skirt selectivity for selective modulation and AF measurement, continuously tunable notch filter from 100 Hz to 5 kHz for signal suppression, high pass and low pass filters for band limiting and measurement of subaudio tones. Other facilities, second RF input of high sensitivity for off-air measurements, so you can measure signals off-air using the antenna socket here on the front. Internal memory for storing complete instrument setups. It talks about the receiver measurements supported by automatic test routines for sensitivity, bandwidth, quieting and squelch, enable fast through service work, because that's another feature that this test set has. It has an auto routine for adjusting squelch automatically, bandwidth, quieting, sensitivity, and then it can give a report out on the printer as to whether that's passed or failed, so that's quite good. Thanks to simultaneous display of all parameters, the transmit radio signal quality can be immediately monitored and additionally evaluated. The optional transient recorder allows for measurement of power and frequency, settling characteristics of transmitters, as shown in the attached menu, as well as recording of power bursts. It talks about the inbuilt generator for VOR, ILS and marker beacon, provides a fast and convenient test of navigational aids, free definable phase increments in VOR testing allow, together with auto run functions, to check the smooth movement of the steering indicators. Fine variation of a DDM value in steps of 0.001 DDM for ILS, and of phase in steps of 0.01 degrees for VOR ensure accurate adjustment of onboard indicators. An AF oscillogram can be displayed in all operating modes and allows, for instance, simultaneous display of bearing signal demodulated by the device under test. Menu is also available for signal generation of marker beacons. It talks about the CMS33 has been developed in close cooperation with many different users. As a result, 3 main operation modes are available for different applications in the avionics field. On one hand, there is often only inconvenient access to the various antenna inputs of an aircraft. That's why the CMS33 is designed and ready to use for off-air measurements. On the other hand, tests have to be performed in confined spaces, e.g. in the cockpit of airfighters. The CMS33 responds by being a remote controllable by a small and handy external control panel. Finally, auto-run programs facilitate complete checks of installations in a few minutes. Impedance matching. AF matching of the different types of transceivers requires a specific adaptation of the different impedances of these instruments. The CMS33 not only measures these impedances, but can alternatively effect an automatic adaptation to the most different values, and thus ensures the required AF level or the correct AF analysis at the device under test. Cell call. The CMS33 provides cell call paging of an aircraft. The coder is conveniently activated by a push of a button, and the required characteristics can be keyed in via the prepared keypad. Auto Instrument Landing System, Autopilot, CMS33 optional. The test of the autopilot, the CMS33 uniquely provides 2 RF carriers, simulating glide scope and localizer in one radio tester at the same time. All standard pairs of frequencies are considered. When the localizer frequency is entered, the appropriate glide scope frequency is set automatically. The relative modulation depths of localizer and glide scope are simultaneously changed by varying the DDM value. SSB. In today's avionic maintenance, SSB testing is a prerequisite for aircraft checks. Thus, an SSB menu has been specifically designed for convenient and comprehensive SSB transceiver tests in the CMS33. SSB-specific measurement requirements are built in, such as a peak envelope power meter. Spectrum monitor. The spectrum monitor permits the synthesizer accurate display of both modulation spectra and complete band alignments. The display of the spectra can be stored and the individual spectral line demodulated. VSWR. Measuring the adaptation of a transceiver to an antenna VSWR provides important information on the receiver and transmitter power of a transceiver, whilst both the sensitivity of a receiver and the power of the transmitter can be determined via conventional RX and TX measurements. The determination of the VSWR is necessary for checking and adjusting antenna matching. The CMS33 permits determining the VSWR easily with the insertion unit taken off. When the insertion unit is connected, the VSWR menu is directly entered and the VSWR as well as forward and reflected power immediately indicated by means of a large analog display. Instrument configuration. The CMS33 is designed as a first-line tester and is integrated in a splash-protected carrier bag, and lateral pocket accommodates the necessary accessories. Such as cables, VSWR insertion unit and user guide. The carrier bag is prepared for the attachment of the optional battery pack, which is trickle charged via the CMS33. This permits operating the CMS33 on site both via the battery and by means of an external power supply in comparison to an internal battery. This has the advantage of lower weight if battery operation is not required. Nevertheless, also an internal batteries option is available. The carrier bag of a CMS33 protects from splash water and conformity, accommodates all necessary equipment. Okay, so to discuss some of the other product refinements, the telescopic antenna for off-air measurement, including the antenna cable, is accommodated in the front panel cover. This cover is designed to simultaneously serve as an antenna base. The antenna cable has spaces for the comfortable and reproducible positioning of the antenna on the runway for controlled off-air tests. It says the AF connectors with special mic tel sockets and the connection for the VSWR insertion unit are integrated in the rear panel of the CMS33 with a battery pack used. These connectors are available on the front panel for battery pack as well. So it shows you there the optional front panel, front cover, and of the CMS33. So you basically got a ground plane. This is all metal, and then this telescopic whip aerial goes about 2 meters tall. It's quite a big, long, thick antenna. It's not a cheap rubbish thing. It you know, it's very well made. It goes up to about 2 meters in height. That's the VSWR head here, which we're going to look at a bit later in this video when we do those tests as well. So anyway, it's got automatic test procedures as well. So it says to prepare the measurements auto test, the only thing to do is to connect the CMS33 to the external operating unit remote control box. To insert the memory card corresponding to the type of aircraft and to provide power supply system. Necessary AF connections are directly applied to the CMS33. An external interface box is not required since the different terminating impedances as well as an automatic impedance matching, are already integrated within the CMS33. It says the remote control box display on there, the user is requested to enter the desired program by means of which individual subsystems, e.g. UHF1, VHF1, UHF2, can be selectively tested, or an overall test of all communication and navigation equipment can be executed. This makes the CMS33 ready for the actual measurements. Exemplary run of an automatic measurement. On the display of a CMS33, or in the case of the remote control box, via the display of the remote control box RCB, the user is given most detailed instructions on which settings to make at the different test items. Example, channel frequency, push to talk, etc. These visual instructions can be supported by acoustic signal output via the intercom equipment. The automatic test is continued subsequently by the user's manual acknowledgement. Once a setting required for the test sequence have been made, the CMS33 starts to measure. The user is then indicated the current measurement of the CMS33 display or of one of the R's on the remote control box, and the result of tolerance analysis can be output via a pass-fail message. In case of non-conformity of measurements with settled tolerances, the user can either repeat the measurement or continue with the tests. All measurements can be stored in the test protocol and printed out later. With the measurements running automatically, the user neither requires knowledge of operating the CMS33, nor does he need to take comprehensive service literature on the instruments to be tested with him to site. All parameters, including the tolerances, are stored on the memory card. So we've got tables showing the different parameters that are set, for example, in an auto test, and what the values are, target ranges, and if they're not met, then it will pass or fail, obviously, depending on that. So it talks about, obviously, test routines, programming and software management. And there's a comical bit at the bottom which is about low cost of ownership, which would be quite interesting to read. All test routines are stored on a write protected memory card. A test routine can be created on a PC, including card reader, at a central office or on site at the test item using the CMS33 directly. It says in both cases, creating a test routine is very simple. When creating it on the PC, the only thing to do is to enter the corresponding IEC bus command. Knowledge of programming is not required. Creation is even simpler directly at the CMS without an external keyboard. Every manual setting or measurement is achievable. It says the small and handy remote control box option allows for the operation in confined spaces, which is this box here, which we'll look at later. Now for the funny bits. Low cost of ownership. The CMS33 is based on the successful CMS family. Its use with numerous aviation control authorities and armed forces guarantees high reliability. Modern design, modular concept and the built-in self-test permit minimal mean time to repair of 15 minutes or less. SMD technology, manufactured according to ISO 9000, and the internal calibration routines ensure a high mean time between failure and maximal recalibration intervals. Thus, a calibration cycle of 3 years is recommended. Then it goes into all the instrument data and specification, which we've got here. So we've got that there. And obviously this section here. So these are all the specifications and parameters. And we've got some more technical information. Sensitivities, power levels, things like that. AF levels. And then the same here as well. And the VORs and ILS specifications. And then on the back page, more technical information as well. Pretty much a rundown of everything we've just verbally described. SSB modes, etc. And that's your lot. So that's that. Now obviously as part of this we get the big service manual, well the big operating manual should I say, which goes into all manner of detail about the product, and obviously all the basic instruments and options, all kinds of comprehensive test instructions, and everything's all detailed in here. So a bit of bedtime reading, quite a thick manual, lots of information on how to make measurements and testing, etc. So it's full of things, even some pull-out diagrams as well in here, which I'll just try and get to. I just saw them flash by, but yeah, where were they? Oh, here we are, look. So you've like got pull-out diagrams and things showing, you know, where the controls are on the front panel and other bits and bobs. So it's quite a fully, you know, featured manual. Auto run printer control, it talks about all the printing options and the auto run bit. What we've got here, VOR ILS generator, all the details about that, and the information on air navigation so that your positioning can be worked out. Landing approach with ILS, lots of information there about the runway and the left marker and the right marker, the height marker, runway side view and runway top view. So you're localizing your glide scope. That's all detailed there as well. How to set up the signal generator, the ILS bit, function principle of the signal generators for VOR and ILS, radio navigational aids. So it's quite a little bit. So it goes on and on and on. Quite an in-depth manual. Okay, so as part of the differences between, say, the Marconi radio communications test instruments, the IFR, Aeroflex, including the HP Agilent range, I just wanted to demonstrate the differences between the RF Attenuator section that's in a ROHDE and SCHWARZ versus what's in other instruments that are used quite widely. And this type of attenuator, that's an RF power attenuator, is from a Marconi 2955 Radio Communications Test set. So basically this deals with the RF input power from the N-type socket at the front and the BNC. So we'll take it a bit and we'll have a look inside, and then we'll do some comparisons. Okay, so we've got all the screws out and everything now, so we can remove the lid, and this is what we've got inside the Marconi 2955 Radio Communications Test Set RF Input Attenuator. Now if we look closely down here, we can see a device here, which is, to explain, the two SMAs, there's one on this side, and then there's one on this side as well, which is just behind this ribbon cable there, just there, look. And then we're followed by two SMB connectors, one there and then one there. And basically the high power RF comes in here from the N-type socket on the front of the radio test set, goes through this pad, and then it's switched by these relays into the correct path then to come out on this SMB. Likewise, the little BNC socket at the front of the Marconi 2955 connects here, and that's then routed through these Teledyne relays, which are RF relays, very expensive relays as well, these are them, and very, very expensive to get. So that's why I always save things, you see, rather than throwing things out. But anyway, the SMB there is the output for that. Now, In any case, if there's excessive RF input fed in either port, then the relay can switch off the input. So it prevents an overload condition. You don't get that on the ROHDE & SCHWARZ CMS series of radio test sets, whether it's the 33, the 50, the 52, the 54. None of them employ that protection. So they just burn out, you see, if you feed too much RF power in, unlike the Marconi. Now, as we looked at, I think previously, we have, and I save these things every time I come across them, but these are second hand, but I have new ones of these. So we've got things like that. So basically this down there is this bit, is that without the lid on, this white cap that goes on over the top. So that's basically the same as this device. So as I say, those are 20 dB pads. So whatever RF input power we feed in there, that'll reduce it by 20 dBs, and then that's what will be present there on this side there. So this is a sort of methodology that most radio communication test sets employ, be it Motorola, Marconi, HP Agilent, and Ritsu Advantest. They all employ this type of methodology. It's only ROHDE & SCHWARZ that tend to do it differently. And of course, in their design, for whatever reason they've chosen, ROHDE & SCHWARZ have designed it so that it's on like a ceramic tile, which obviously, and in our case, and has been previously reported by many other owners of ROHDE & SCHWARZ test instruments, they crack. So, you know, that's a type of thing that you can expect. But this is from a Marconi 2955 radio test set. So we've got a little thermal sensor screwed onto that. So obviously if this gets too hot, then it'll report an RF overload as well. But if the RF power coming in is way more excessive than it can take, even before this heats up, this relay will isolate the RF outputs. So it's really important, is that very important, that we have this kind of protection on the front end, on both the high sensitivity port and the high RF power TX port. Now we've got a modern radio communications test set, which is from both an analog and a digital format, from the 2960 series of Marconi radio communications test sets. We have the same methodology again. We've got the main RF input that can take 150 watts in this little box here is one of these, and then we've got all the other circuits, relay switching, mixing, sampling and everything that takes case afterwards, which is hence the reason why we've got the SMAs on the top. But one of the main things I'd like to point out with this design, both on these different types of radio communication test sets, is the amount of metalwork and the heat sinking and the ability for the device to keep cool. When you compare that against the ROHDE & SCHWARZ radio test set, the ROHDE & SCHWARZ I think is underrated with regards to its thermal heat sinking capability. I mean, even the Marconi 2955 is rated to take 75 watts continuous, the 55A and 55B models, and this is the module that's in there. So that's bolted obviously onto the side of the instrument, and that panel there is heat sinking onto the metal casing of the test instrument, the chassis of it. But as well as that, we've got these little heat sink things as well, which go on to keep it cool as well. And there's a lot of attention into the thermal properties that occur when dealing with high RF powers. And this is what, when we look at the CMS54 in a moment, which I'm going to demonstrate along with the CMS33, we'll see the differences between them. But the main difference, of course, is the cost, because these parts are very cheap to replace. And as I said earlier, KDI, there's one of these in here, I think that's manufactured by KDI. That one there, which is extremely, you know, popular manufacturer of these types of RF pads. But basically the gist of what I'm saying is that these are readily available at cheap prices. You know, you might pay, I don't know, £50 for something like that maybe from KDI, but something like this is easily replaceable at that cost. So there's a big difference between paying, say, £50 or £15, whatever, depending where you buy them from, because they are quite cheap in some cases, than £600 with ROHDE & SCHWARZ. And as well as that, the 2960 series attenuators, they go up to over 2 gigahertz, because one of the options on the 2965, 66, 67, 68 radio test sets is you can have them cover the cellular bands as high as 1.8 gigahertz for the cellular options on there for GSM and DCS or cellular systems. So again, these are, you know, an LTE cellular, so the frequency ranges of these attenuators far exceed by at least 1 to 2 gigahertz higher than the CMS radio test sets RF attenuators do. So I think really what I'm trying to say is I think ROHDE & SCHWARZ have over-egged the pudding, and I think in an effort to make their attenuator more specialised than other manufacturers, it's actually created a problem with thermal cracking. So, you know, that just goes to show you, when you try and reinvent the wheel, sometimes it doesn't always work out. Anyway, we'll crack on and we'll compare now with the other radio test instruments. Okay, so what we've done now, we remove the RF attenuator module that was sat here in the back, that connects to this rigid coax that comes up to the N-type RF plug here. And what we've also done is remove that little tiny attenuator, the square one that's bolted to the chassis side rails that you might remember, that was right at the back, that this connects to first. So anyway, on the bench, we've got them now. We're a bit of a devil to get out because they're quite compact and screwed in fairly well. So this is a little module that the N-type socket on the front of the RF test set connects to first. It connects to one side, and the other side then goes off to this module here. So that's some kind of power attenuator, which we're going to look at. And then we've got this, which is the main RF attenuator module, which is identical in appearance in every way to the one employed in the CMS33 radio test set. And from what I've seen of the other models of radio test set, it's a common part shared amongst all the CMS series of radio communication test sets, no matter what model number you've got. Now naturally, when this is in the CMS34, which you'll see in my CMS34 repair and update video, this can only take a maximum of 50 watts on its own. So any more than 50 watts, then it can damage the input attenuator resistor. So hence the reason why they've employed this. And we'll sweep this as well to find out what RF attenuation this provides. But anyway, I've taken the screws out of both modules so we can have a butcher's. But before we do that, this SMA socket here is what connects to this. Or on the CMS34 test set, that's where the N-type on the front of the test set will connect to this SMA. This SMB socket here is for the TX monitor system to connect to. So the modules for the spectrum analyzer, the TX monitor for deviation, frequency count, etc. connect to that socket there. And then down here, this SMA is what's used for the RF signal generator. So the RF signal generator signals fed in there. This is a potentiometer that sets the RF power that's being read by this module. And these two connections here, one of them is for the RF power DC level. So after it's undergone attenuation within this module, it then gets rectified and then smoothed and then passed out as a DC voltage, which is directly proportional to the RF that's coming into it. Now, because it's been attenuated massively beforehand, it means a diode is more a chance of surviving than dealing with direct power coming in. And then the other connection is the temperature compensation diode. So as the attenuator assembly heats up, then that diode then compensates the difference in characteristic on the main measuring diode and keeps track of it. So it's quite well made module. It's a lot of thick metal, it's quite heavy. Anyway, that's what looks inside now. Now I can see on this particular model of test set, RF attenuator, it's slightly different in appearance. The CMS34 is exactly like it, but it's white, and it's made of like some kind of glass ceramic substance. But this I can see straight away has got some extra mounting lugs here, which there's two on the CMS54, but it's the actual back plate that the resistor's soldered down to. The tile is soldered to, which is bolted down on the CMS54. Whereas with this, there's these extra copper, brass, whatever, like bars there as well to cushion it. Must be to provide extra heat dissipation as well from the edges of the tile. Now, everything else about it is exactly the same as what's in the CMS54. So I think they've made an effort to try and improve that resistor. And so if we take a closer look at it and examine how it works, if we go right in and zoom in on this resistor element here, let's have a look and see whether we can see some more detail about it. Just get the camera steady, because it has a habit of moving by itself on this mount. Right, so now then, we've got at the top here obviously the RF connection coming in from the what will be the front socket of the N-type socket on the test set, either be another attenuators in this case or directly as in the CMS54 series. It then goes through a bit of a snubber here, obviously for damping out any harmonics or spurious or undesirable elements at certain frequencies. That gets dealt with there with some RF absorbing material, which is this black stuff. It's just like a cushion that's soldered on top. Then the track goes this way through some more RF absorber before it enters what is the first of the half of a pi attenuator. This entire attenuator here is 16 dBs, and then there's another 10 dBs, I think it is. That is the 10 dB attenuator there. So the two together is 26 dBs. So basically, in its present form, RF comes in from the top, goes through this part of the resistor element, and then going to a central junction before going through another resistive element, and then going out to what is this is where the received signal generator input is fed in. And then the other branch from the central island here branches to the right to this central island. This is a resistive element, and then there's a resistive element down to ground. This is RF ground. Likewise, junctioning from the centre to the top, we've got another resistive element there, which then ultimately goes off to the second connector, which was the SMB we spoke of earlier. Now you might just see on the camera there's two black dots there under some kind of like epoxy. They're the actual Schottky diodes that are soldered on the board. It's probably just the actual diode die with the bond wires, and then they put an epoxy blob on top instead of using a separate leaded component to keep obviously parasitic inductance low. They've got a capacitor here across to RF ground to smooth off the RF signal properties that come through the diode on the half-wave rectification, if you like, and then that then gets passed out then to the connection that goes out to the feed-through capacitor, which is one of those wires, the two wires that I showed you. This is a temperature compensation diode, and again that's its feed-through capacitor point there. Now we also have here, you might notice if I just move it forward a little bit, we've got a number of relays here, as we can see soldered in, but we have a relay here. So if we just want the 16 dBs of attenuation for low RF powers that are coming in, that gets fed through this relay, connected across, and then obviously this is a signal generator coming out that way in duplex mode, for example, or when the receiver's just in receive mode, for example. So basically this is the collision point where the transmit signal coming in would collide with the receive signal going out, and that all happens in this area here. So the RF signal present here is very, very low, probably in the order of milliwatts before it reaches this point, because obviously that power fed back into the received signal generator would damage it otherwise if it was high RF here. So that has to be brought right down. And then what we have here, we have another switched element as well within the relay, which switches this pad in. Now this pad is actually separate to this bit here, but what happens is, if they need this pad brought in for extra attenuation, what happens is this relay would click into this position here. So the RF signal coming through to the received side, as well as RF power coming back this way, would then be attenuated by another 10 dBs. So if we get high RF level coming in here, obviously the level of RF present at this point is going to be too much for the received signal generator output to cope with, and so the reverse RF power that's coming back from our transmitter under test this way would damage the received signal generator final amplifiers. So how they combat that is, when the RF level gets above a certain level coming in here on this attenuator section rectified by this diode, it'll reach a decision making point where it has to click this relay in, so that this 10 dB pad here comes into play. Thus there's a total attenuation there of 26 dBs, total attenuation through this relay, this switch relay. So that's how it deals with that problem, you see, of the collision between the RF going out and the RF coming in. And so that 10 dB attenuation is switched in there when we need it. But basically the pi attenuator for the first attenuation stage for the transmit power being measured is these elements 1, 2, 3, 4, 5 resistors. So essentially we've got a pi attenuator. The ROHDE in the service manual refer to it as a star attenuator in a star configuration. But in the problem we have on the CMS34, we have a crack that goes from here right the way across, and it literally crosses this resistive element here, which is on the right. It sort of goes that way, and what it does, it's fallen over, what it does is it crosses this, sort of goes at an angle across, crosses this, but doesn't break this connection here. It goes straight across down. It's almost like it starts about here, actually, if I remember rightly. You'll see it in the CMS54 repair video I did. Starts about here, goes straight through this element here. I think it is an element anyway, or it could be the black bit in the middle, but it goes straight through that and carries on and just comes to here. So basically anything left of a crack is fine, and that's the reason why when we're in receive mode and we're receiving a signal, well, we're sending a signal out to a receiver, so we're generating an RF signal to come out through here. It travels through this part of the attenuator and out to the N-type on the front of the test set without an hindrance. It's only when the transmit signal comes in and it needs to be attenuated and then measured here with this diode, it can't do it because the track's broken, you see, across here. Now, I have actually thought about, on the CMS54, getting a big beefy soldering iron, removing this component altogether, put it on a piece of wood, getting a big chunky soldering iron that I've got, which is for big boy soldering, heating this back plate up so it literally melts all the solder and this tile starts floating, and then break the two halves apart, you see, get them under the microscope and see whether I can do a track repair. But I think I'm clutching at the straws there, because I think it'll be unsolderable, this area. I think it'll not be possible to solder there. Plus it'll have beryllium oxide, which is a highly toxic substance as well, so it's not worth scraping and machining and messing about with. But yeah, I'm not sure, you see, if the resistive element is this black stuff in the middle or it's the two green things on either side. It could be either, but there's another one going there, look, it could be these green things are actually metal oxide or something which is bonded. I'm not sure, but obviously this black strip in the middle is a darker colour than the outside substrate. But yeah, yeah, it's just a shame really that the fault that I had is broken right through the middle of the RF attenuator resistor. Now that German guy, who's I think works for ROHDE and SCHWARZ, who did this really good article in German that I showed you on the CMS34 update video, his was very lucky because his crack went from here, it went across this way to there, so it was this corner here, it was across the corner. So all he did, he had a broken connection about here where the scalpel blade is, and he just bridged it with some solder, you see, and then did a really good job at doing it, because naturally when you try and solder on this, it dissipates the heat away straight away from the soldering iron. So he had to heat the whole thing up, get the I think the back plate quite hot on a back plate heater, so the whole thing was stinking hot, and then he had to then try and solder here so that the whole wafer was the same temperature as his iron that he was going to solder here. Otherwise he wouldn't have been able to bridge it. But yeah, he was quite lucky. But this is the problem with these resistors. The common fault is the crack, and it's with the design of them being quite poor, and the fact that they can't dissipate the heat away quick enough from the resistive elements, and then the substrate cracks. And that's my beef with ROHDE and SCHWARZ with this. You know, I've had a few rants now about it, but I think it's time ROHDE and SCHWARZ looked after the customers and realised that when these things happen, it's through no fault of the customer, and that they should be making this part affordable, and perhaps even replacing it free of charge. I mean, after all, it's widely known this is a manufacturing defect at ROHDE and SCHWARZ making. So, you know, come on ROHDE and SCHWARZ, let's get the, you know, let's smell the coffee here, let's get this part sorted for people. But yeah, so that's a little rundown of that. Obviously we've got, these are the pi attenuator resistors I was telling you about, and the receive signal generator that make up the different pads. There's another pad there, look, and then there's another pad here as well, you can see. So all these pads are all in place so that you've got different amounts of attenuation switched in or out depending on what signal generator level we want coming out. So naturally we've got to attenuate any transmit RF coming in this area down substantially, and then if necessary attenuate it again before it reaches these surface mount resistors, because these surface mount resistors can stand no power whatsoever in terms of RF energy. They'll just burn up, so they'll go into black charred state. So that's why we've got to get the RF level down. It doesn't matter if we're in duplex mode or we're in transmit mode, TX mode only on the test set. Doesn't matter. The fact is the RF, before it reaches this track here, has got to be very, very low indeed. Super low, in order for it to not burn these resistors out, or also track back to the RF signal generator input here on that socket, that then would ultimately damage the amplifiers in the RF signal generator section. So that's a little rundown. I haven't had any problems with these relays on any of the ROHDE and SCHWARZ test sets yet, but no doubt they can fail. Not had any resistors burn out yet or anything like that, but it's just been this damn thing. But I can see on this one though, because it's probably a newer test set than the CMS54 I've got, they have attempted to try and alter its design. These two bars here weren't present on the CMS54. This was white colour, so it's totally different design insofar as its substrate material. It's changed. So I think they've known about it, obviously, as a production fault, and they're trying to address that thermal problem, that thermal cracking. Okay, so what we've got now, we've got this little attenuator here, made by ROHDE and SCHWARZ, obviously. This is where the RF input power connects into on the left hand side, because it sort of bolts in, remember rightly, bolts in sort of that way onto the chassis there when it's turned on its side. So RF power comes in on the left and goes out on the right. So anyway, inside this is what it looks like. So it's obviously quite a very unique part, obviously, just like what we get with the other types of RF resistors that was shown earlier with the lids on them. So again, it's this white ceramic substrate that's bonded to the resistive elements. So as we can see there on the left, where the RF comes in on this side, it goes in and meets with the resistive element, which is right in the middle there. Now if I just get a bit more lighting, might be able to make it a bit clearer, a bit better, but basically it comes in on the left, it's that resistive element in the middle, and then you've got two resistive elements which go vertically to the top and to the bottom, and they are the pi. Essentially those three elements, the big square in the middle and the top and bottom, form the pi attenuation, and then the output is on the right hand side. So that all heats up obviously, and that's going to dissipate heat away quite quickly. That's why it's solder bonded all the way around the edges there, the tiles, and no doubt it underneath it's soldered as well down to this enclosure. Now it doesn't tell us on the enclosure what the RF sort of attenuation is. There's no mention of it at all. I would have thought if that resistor in the switchable RF attenuator can only take 50 watts maximum over the or continuously as rated on the CMS34s, and no doubt on this as well, this resistor element here can only take 50 watts continuous. It might be rated about 60-70 watts peak, something like that, but that's definitely got to get, this has got to get the power down. Well, if we're talking 150 watts rating, which is what we were discussing earlier, the spec on the CMS33, you'd have to get it down by at least, well, 3 dBs would be half in the power, so it'd be 75 watts. 450 watts, half of 150. So it'd have to be at least probably 6 dBs, I would have thought. So it'd get it down to 70 odd watts. But it depends on how, yeah, if it's 6 dB, 3 dBs will half it to 70 odd watts, and then half 70 odd watts again for 6 dBs. So every 3 dBs of attenuation we had with half the power. So it's possible that 6 dBs might be a bit too much, because if you think about it, that'd reduce its power well below the 50 watt mark. They might have chosen to do that, but they may not have done. So it could be that this is a finely manufactured attenuator. Instead of buying them off the shelf at 3 dB steps or 10, 20, 30 dBs in 10 dB increments, they tend to be made, these attenuators, in 3 dB increments, or 1 dB increments, or 10 dB increments as well. So that's generally what they are off a shelf. But this being a bespoke design from ROHDE and SCHWARZ, they may have chosen to have a specific attenuation level rather than just an off-the-shelf variant of it. So this could, I certainly think this is going to have a greater than 3 dBs attenuation, but possibly less than 6 maybe. But we'll see, because it all depends how they've done the design. Obviously whatever attenuation factor this provides, in addition to this attenuation, then the software in the test set would have to take account of all this attenuation. So when it reads the RF power correctly, until the RF signal generator output is compensated accordingly, so that it can overcome these attenuations, so the level that's expected on the output is correct. So right, so what we've done, I've just set the spectrum analyzer tracking generator up. I'll just see if I can hold this straight. This has got a nasty habit of falling over. We've connected both the track gen output and the spectrum analyzer inputs on a short loop cable together. We've calibrated the tracking generator and normalized it so that on this frequency of 500 megahertz it's providing a 0 dBm reference output, which has been read on the input, and it's reading 0 dBm. If we just go in on the spectrum analyzer, if we can get the damn thing to focus, because it's playing up. Right, that's a bit better. Okay, Okay, so we've got the 0 dBm reading here in this corner up there. We've got the spot frequency of 500 megahertz, which I've chosen. We're not going to bother sweeping a wide frequency range because I don't think there's a necessity for doing that. So I think what we'll do now, we will get our friend the RF Attenuator, and we will connect it up. Now let's have a look here. Our butchers. So on the left side of this is the RF. I've put an adapter on here which then connects us to an SMA from a female to an SMA male. We'll just disconnect this. Okay, connect that onto this side of the resistor, and then all being well, if it bites and gets going, this damn SMA, it's always a devil. Too tight tolerances. Right, that's nice and snug, although I should nip it up really with a spanner, but just finger tight for today. And then we'll connect this little thing down there as well, get that going, and then we'll see what it's got. Right, okay, so we'll have a look now what it says on the screen. So it looks like 3 dBs, 2.96 dBs, minus 2.96 dBs. So yes, that does look like as if it's given a 3 dBs of attenuation then. So it would half the power then from 150 watts maximum down to around about 75 watts. So obviously that's what we're doing here, it's halving it. So it's minus 2.97 dBs. I wonder if I can just adjust the span. Oh, is it now? Frequency, start frequency, we'll say I've 1 megahertz then, 1 megahertz, and the stop frequency we'll have at 1 gigahertz. So we're starting at a 1 megahertz and we're stopping at 1 gigahertz, and it's quite consistent. Oh, hang on though, minus 13 dBm, 13.91 dBm. Oh, I've got to calibrate it again, haven't I? That's why. Let me just calibrate again, because it's obviously off. That's the thing, you see, between changing settings, you've got to calibrate again. Otherwise, it's just got to get this damn thing off. So quite a devil is this SMA. Just get that sweet spot where it comes off. Right, we'll connect the cable back up to the input, so we've got that loop again. We're 10 dBs off, so I need to go to source, track gen, normalize. Right, now we're at 0 dBm again, 0 dBs. Now I can then go and connect this back up to the attenuator, and then we can see what's going on. Let's have a look. I have a little spanner somewhere for tightening these up, but I can't find it. It's always the case when you need something, you just can't find it. Little spanners go missing. Right, so we're screwing it onto the front of a test instrument, the spectrum analyzer. If the SMA will bite, which it will, yep, there we go. So quite a consistent frequency response over its over that range there. So we're starting at 1 megahertz, obviously stopping at 1 gigahertz. The center frequency is 500 megahertz down the middle, and then if I just move the marker around and let's see what so it's more or less keeping that 3 dBs quite consistently right up to the end there, right up to a gigahertz easy. Yeah, it's nice and linear, it's nice and straight. So let's have a look. Let's keep it going back down to 1 megahertz. So yeah, it's, as you can see there, absolutely fine, no problem at all. So it's a 3 dB attenuator then, which means that obviously it'll reduce the power by half. So that's how they've chosen to design this particular test set, with a 3 dB pre-attenuator before it gets to the main attenuator block. So that proves that, in case you didn't know. You see, I can't help but thinking here that ROHDE and SCHWARZ have gone to an awful lot of trouble to add all these attenuators, you know, just to deal with 150 watts. Now, this is the Marconi attenuator that we had to bits earlier in this part of the video, where I showed you those resistors that are inside. The Marconi 2955 radio tester is long established now in the world of RF and electronics, radio frequency engineering, maintenance and repair radio systems. These are, you know, the bread and butter of the radio test set world. Now, this RF attenuator is designed to take 75 watts continuous, but about 150 watts peak just on its own, and it can actually handle slightly more than 150 watts, about 200 watts actually, continuously, but it will get quite warm. Now obviously it's bolted down to a chassis rail, it's got a heatsink on the top as well, but we're talking here, when this was designed by Marconi Instruments in the 1970s, the capability to be able to deal with high RF output powers quite effortlessly, whereas when we compare that against ROHDE and SCHWARZ, we've got all these problems, you see, all these problems of cracking resistors, having to add extra attenuation, all these other factors to just deal with 150 watts, whereas Marconi sort of had it, you know, nailed on in the 1970s. And really that just shows you just how advanced Marconi were in their design of radio test instruments. And when we go further into this CMS as well, you'll also see there's no protection on the well, there isn't here, look, there's no disconnect relay. So if the input power to that attenuator is exceeded, it won't disconnect that attenuator like this does from Marconi. That disconnects the RF input. If it gets beyond a certain level, that's it, just clicks off, so it doesn't damage the instrument beyond that, you see. Whereas ROHDE and SCHWARZ haven't thought about that. So I don't know what they were thinking, but naturally if the RF power coming in there into either of these modules is excessive, they'll burn out and perhaps damage the rest of the instrument. And it's the same with the low power connector as well on the front of the ROHDE and SCHWARZ. When we get into this module in a moment that connects to this, you'll see that there's no RF protection at all. Indeed, there's just a pi attenuator resistors on the board, which are these resistors here, these three. There's a very similar arrangement in one of the modules in the CMS33, 54, 50, 52, etc. radio test sets, but there's no protection, so you'll go feeding high RF output powers from a transmitter into the wrong port, and you're going to burn out the instrument. Not only that, the pi attenuator will burn out, but there's also some of these HP, I forgot what they're called now, the gas FETs, I think, amplifiers, wideband amplifiers that are after it on the sensitive receiver input on the CMS series of test set, and they burn out as well. And it causes no end of damage, and you can get varactor diodes that pack in, and pin diodes and all sorts of things. Causes thousands and thousands of pounds of damage to a test set, and it shouldn't do, you know. So you know, when you consider Marconi Instruments back in the 1970s and prior to that E&D, but certainly with the 2955 design, were way ahead of the game in every respect than ROHDE and SCHWARZ, and likewise ROHDE and SCHWARZ came about with these test sets many decades after the Marconi 2955, and yet they'd still not caught up with the ideas that Marconi had already implemented in ways of protecting the instrument. And that's a common theme in Marconi instruments. You'll find IFR, Aeroflex, and indeed Agilent test equipment, where they do have that protection built in. But ROHDE and SCHWARZ don't seem to do that, and I've never understood why. Obviously the result of that is you blow your test set to bits, and that's it, you know, you throw it in the bin. But as far as this is concerned, Marconi, you know, definitely ahead of the game. Cheap off-the-shelf components, a lot cheaper than the bespoke designs of ROHDE and SCHWARZ. And I don't understand why ROHDE and SCHWARZ in this case have gone to this attenuator design, which is their own, you know, a 3 dB attenuator that you can buy from anywhere, because they haven't managed to design one of these attenuator resistors that can handle 150 watts on its own. Whereas Marconi, Agilent, Aeroflex, IFR all have done that prior. So it just shows you that ROHDE and SCHWARZ aren't as ahead of the game as what they reckon they are when it comes to the latest technology and everything else. And that proves it, really. It's fact, you know, it can't be argued with the fact that they're having to use all these additional add-on bits just to get the RF power down, when Marconi does it within one module, and protects the input too, which ROHDE and SCHWARZ doesn't. So that just shows you the design methodologies are different between the manufacturers, and that might be the way that ROHDE and SCHWARZ have chosen to do it, and fair enough to them. But it doesn't mean that, you know, as far as the customer's concerned, they're going to be happy when it blows up, you know. So this is what you've got to consider when you buy these instruments. Okay, so this is the module now taken out that goes in the back here, that deals with all the signal processing from the transmitter, etc., and the output amplifiers as well, output stage. So we've got obviously the from duplex, whatever synthesizer, from attenuator, and then from synthesizer, and then on this end here we've got another from front panel, which is where the BNC connects to his X604, and then from to attenuator as well. And then obviously we've got a 250 to 1000 megahertz from synthesizer, and 0.4 to 1000 megahertz from repeated option. So as an option connects into X607. We've got some adjustment points on the front as well. Just a couple really, about 3 holes there to adjust various things like the RF level output, things like that. So min max output level, minimum maximum AM modulation, and then this one is min max level offset as well, part of the calibration sequence. So we'll have a look inside the module and show you the pi attenuator. Okay, we've got the module apart now, all the screening cans. It's quite well put together. The screening can on the rear's got captive screws, so you don't lose them. But the main cover on the front, which is this, the screws you have to put to one side because they're not captive. But anyway, the top part of the board is visible, and as we can see, it's quite a bit to it. Make no mistake about it, these relays are not cheapo sort of ordinary DC relays that you get in most gear, although they look like it. They're not. They're actually a metal cam under this plastic skin, and they are latching relays as well, where they just need to be, some of them, like on the RF attenuator, just need a pulse of DC, and they'll latch one way and then latch the other. And the screened cans underneath as well, so that they're actively screening RF signals. So the proper RF relays, they're not rubbish, you know, they are good quality RF switching relays that they're purchased. And there's quite a few contacts on them as well. There's not just one set of throw contacts on them, there's several pairs on some of them. So this is the top part of the board, bog standard components and things. as we'd normally expect to see on most test instruments, but the main area of interest that I'd like to focus on is this that's underneath. Now X604 is the socket which goes to the front panel socket, the BNC on the front of the instrument, which is the one that deals with off-air signals, high sensitivity. So that will be X604, which is this one here. So if we look at this in relationship to the connectors, X604 is the one that goes to the front panel, so it's this one. Now we can see from at the top here that it just seems to disappear, the contacts there, they just don't seem to go on the top of this board. It's obviously through the bottom, whereas this connector here, we've obviously got some traces going off these that go to different components on the top. So X604 goes through to underneath. Now if we look underneath here, we can see, because there's lots of nice gubbins under here, there's the centre pin there of the X604 connector. Now if I zoom in on that, we can see that it goes through a series capacitor, RF capacitor, DC block if you like. So if we were to feed any DC on the BNC on the front, then it wouldn't damage the pi attenuator, which is formed by these three resistors here, these surface mount resistors. Now on the CMS34 test set that I've got, these are all burned up because somebody's put 25 watts in. But what happens is it comes straight in off the centre of a connector and goes straight across this capacitor, hits the first resistor in the pi network. Then you've got the series resistor. So the first resistor is between RF signal and RF ground, or ground, and then obviously we've got the series pass resistor there, and then the next resistor, which is on the next part of the end part of the pi, is between the signal output of that resistor and RF ground. So that's why we're getting the pi attenuation. Then it goes into one of the relays, you see. So naturally we can switch in and out this socket. Now this relay here is the relay that switches between what the signal pass would be from the RF N-type plug after it's been attenuated down, and the output of that attenuator module comes into this and goes to a gate on this relay, a contact on this relay, as well as the low power high sensitivity port comes into a separate contact on this relay. So this relay that's soldered here switches between input 1 and input 2 on the selection menu on the test set, and then it goes off then for signal processing. But before it does that, what it does, it pops on top of the board on the other side, and we have these these attenuator pads down here. You can just see there's a lot of pi attenuators made up with these chip resistors, and these switch in different levels of attenuation. Now one of the components that does go when you feed too much RF power up it is this FET, gas FET device down there. Now it is actually a known problem, is that, and I do have some of those in stock to replace them, but they do often pack in those, especially when somebody feeds, you know, an incredible amount of RF power up the front end. It then leads off. Just have a look a bit closer here if I can get a bit zoomed in. Let's have a look. Just come back out a second, let it focus because it's a bit dodgy, this camera. Right, so it goes through there. Yeah, you've got a signal path through onto the underside again. So we've got RF grounds top and bottom there. We've got an input on the left, I think output on the right, or the opposite way around, and then it feeds off then. We've got different feed through components on the left which then give a correct biasing, etc. Before it gets fed up right up to this stage here, before then it progresses beyond this stage then. And looking underneath, if we have a look at these components. Got all these. We've got this miniature coax then as well. We've got like a mini coaxes. You can see them here. They just go through and are soldered onto different plates, and the like a semi-rigid coaxial cable. And then we've got the same down there as well. We've got a inner connecting off down there. So after all said and done, once this attenuator, step attenuator's done its thing and amplified the signal appropriately, then it gets passed off, then off to right the way around and off to different circuits, different parts of the system. So you can sort of follow it round, you can trace it round. So yeah, there's no protection, you see. That's the main point. Once the signal comes in through there on that central connection there from the BNC on the front panel, it's DC blocked, which is fine, but then we've got no protection. So straight away, too much RF power, blow those resistors, and that's, you've got a permanent fault then. So that was the beauty that I was trying to get at with the Marconi design, the fact that it's got an RF disconnect relay, which would then disconnect this should the RF power be exceeded. Clever things, you see, that Marconi think about, and also other manufacturers. But of course, if you look on the top as well, you will see, I think on some of these connectors anyway, I think it's mainly, where was it now? I did see them earlier. Not sure if it's those. Some 0 ohm resistors. Not sure if that's one down there. I think it is. I can't see through the camera, you see, the screen's too small, but some of these have been 0 ohms as well. I think I saw some up here as well. Let me just have a butcher's. Yeah, there were some 0 ohm resistors that I've seen in line with the signal path somewhere. I'm just trying to find them again. Let's have a look on this side. And I think they must be on the top. I just have a look on my magnifier. Just can't see through the camera. Let's have a look. Yeah, like this one here. I'll put my thumb on it so we can see it. Where is it now? There we are. That's a 0 ohm there, look. A 0 ohm. They're like in an effort to protect the circuit. That's not a 0 on that one. We've not got a 0 on X604, which is the one that we need to protect the RF input. But then down here, is that a 0? Yeah, another 0 there. Look, just bottom left of this relay, I can see. So that's another protection. That's not a 0 there. That's a proper device. Is that one proper RF resistor? So yeah, they've not employed that philosophy, you see, on there, have they? You know, where the signal comes in on here and doesn't go to a 0 ohm resistor. Mind you, it don't matter anyway with 0 ohm resistors, because they need a massive avalanche of current before they'll pack in anyway, which will have blitzed all this by then anyway. So, but there should be some kind of a protection. You'd think they'd use like back-to-back Schottky diodes across it, so that, you know, if the RF voltage goes higher than about 0.7 of a volt, then what it'll do, it'll clamp it, and then maybe have a resistor, a low value resistor prior to the clamp diode, so that if the RF current is massive, then it would burn the resistor out, and the clamp diodes would prevent the rest of the circuit then from getting damaged. Because, as I said before, these resistors pop in those microseconds before they burn out. That massive RF power avalanche goes through this relay and ends up at that FET and blows that device, you see. And they're quite expensive of those FETs as well, but thing is, even more probably if you're buying from ROHDE and SCHWARZ. But this thing is that the most sensitive part of it, really, and where it's more prone to damage. So quite interesting, very interesting indeed. It's always nice to look at these things and analyse them further and find out what's what it is that's, you know, that's goes wrong with them. Right, so what I've done to help anybody who's in that terrible situation as I've been in, where this pi attenuator's gone fizz bang, and then of course you can't read the resistor values because the resistor values are written on the top of the surface mount resistors, and then if you can't get a diagram or service manual, which is normally the case for ROHDE and SCHWARZ, then you don't know what values they are, and you can start, you know, trying different ones out and put the module back in and trying to find out whether it was a 3 dB, 6 dB, a 10 dB, a 20, a 30 dB attenuator, and you can keep faffing about until you go blue in the face just trying to work out what it is, and obviously trying to get the RF level correct, you know, obviously because it should read right through the BNC as well as on the N-type. So that's the values. We've got a 2000 ohm resistor or 2K across the signal path after the capacitor to signal ground. Then we've got in series as part of the Pi network the 27 ohm resistor, and then we've got a special resistor value which is not normally seen. You might have to make these up using multiple chip resistors paralleled on top of each other in order to get this special value of 2430 ohms. So this is where, if you watch my attenuators video that I did, we talk about having to have exact attenuation. Otherwise, just a small change in value of resistor, because it's not the preferred value of resistor naturally is 2430 ohm. If you don't get the last bit correct, you know, you put a 2400 ohm resistor in a 2.4K, that 30 ohms makes all the difference when it comes to the actual RF attenuation that takes place. So you might have to stack, unless you can get a special 2430 ohm resistor order, which probably somebody will make them and supply them obviously, but you might drop on. But if not, then you'd have to select other resistors and put them into parallel, so that they are equal to 2430 ohm, and you can do that, you know, it's just a lot of faffing about, that's all, and it can get a bit ugly stacking things on top of one another and soldering and what have you, but it will work. But anyway, that's the values of resistors that you'll need if the input to X604, which goes to the BNC socket on the front, has an excessive RF power fed up it. So hopefully that'll help somebody, and you know, if I get that problem, I've just read those component values off of resistors directly on there with my magnifying glass, so best of luck. Okay, so here we are again now with the bottom of the unit. I've already replaced this foot here. So a common fault on these, that these break off and you lose them. I have plenty of spare ones of these that I save. Anyway, quite easy to fit once you get them off the other instrument. There's two pegs that are driven in these holes here from this side when they're clipped back into place. These are the pegs there. Basically all that happens is these round fingers that go into these holes clip in, but to prevent them from being pulled back, you drive the pegs in. That's all you do really to fit them, if ever you have this problem yourself. And by the way, you can always fit, because they've put these nice little holes here, you can get these little rubber feet with the screw nut and bolt through them, and you can fit them to these test instruments. So you know, there's also holes provided for those as well if you just want standard rubber feet. But it's a shame they didn't make these better, more rubberized, rubbered, you know, rubberized components, because they're brittle as anything and they smash and break easily. But anyway, to replace them, what you do is you just drive them home, the clip in like that, and then you take your pegs and you drive them in from this side, not the other, until they're flush with the surface. And that's it. That peg's a little worse for wear, but I think it'll do. Not sure if it goes in that way, so there. So that's it, you see. And then of course, by having the pegs driven into the middle of these feet, it splays these fingers out, which makes them bite into the outer circle, stops them from being withdrawn later on. So that's that. Okay, so one of the features on this radio test set as well is a sensitive receiver option, which is installed on these as standard, where we can pick up very sensitive low RF signals on this port here. When I say very sensitive, what I mean is in the terms of microvolts. So it's suitable enough and sensitive enough to be able to pick up off-air signals from a whip aerial or an external antenna, if you've got one where your workshop's located. Makes it really good for field work as well, where you don't have to intervene or interrupt the RF paths on radio equipment in order to, say, for example, check a hilltop repeater site or an aircraft or a vehicle or a boat. You can just literally plug an antenna into here, key up on the radio and perform transmit tests into the test set just on an aerial. So it's a non-intrusive way of making measurements in RF systems without actually having to break the RF path between the transceiver and the antenna. So it comes in real handy, especially in avionics circles, marine, land mobile applications and base station type scenarios. But unlike other radio test sets, the ROHDE and SCHWARZ CMS series boasts quite a high sensitivity on this port, whereas other radio test set manufacturers, some of which don't produce a port sensitive enough to pick up off-air signals. They will pick up local signals within the workshop. So if you're using a handheld radio in the workshop and you're transmitting to it, such as something like this, for example, if we were, say, maintaining a handheld transceiver in the workshop and we had an aerial connected here, when we keyed up on the radio, because the signal is in such local proximity to the test instrument, it will pick it up quite easily and obviously then display it on the measurement system. But in this particular case, we've got the capability to connect an aerial here and pull in signals from further afield, from distant broadcast stations, transmitter sites, etc., whatever that could be. So that makes it a really useful piece of equipment to have. So how we set that up is we just simply go to TX test, and from TX test then we input the frequency. Now, one of the nice features on this test set as well is you can set very fine increments. It's not unique to ROHDE and SCHWARZ. Most test instruments allow that facility. And how you set an increment is done through the VAR key down here, which is for variable or VAR. So I'll show you how we set that up. But first of all, we need it on set RF instead of counter. We'll enter frequency, and I'm going to choose BBC Radio 4, which is a local radio station to me. Is it on 93.7? I think it is, yeah. So I think it's on 93.7 megahertz. So we've set that. At the moment it's reading AM, which I don't want, so we need to go to RX test, set the mod to 1.5 kilohertz, so any kilohertz frequency, just so that it gets rid of it. You have to be a bit careful with this, because if you don't press the mod 1 instead of AF1, then it doesn't set it right. So that changes it to kilohertz instead of percentage. That's a domino effect, a knock-on effect then onto TX test, obviously. So now we'll see that we've got kilohertz displayed here instead of percentage for AM modulation depth, which is what we're wanting. Of course, if you're wanting to receive AM signals, then yeah, you do the reverse of that. So that's reading percentage for amplitude modulation depth. So we've set that now to receive FM 93.7 megahertz. We're going to change the input down here from input 1, which is this, to the high sensitivity port, which is input 2. So we'll do that now. Flick that across. I've heard the relay go inside, so that's all nicely done. The D mod side here, we've got the down arrow again, which we can now look at further information on that. So the D mod is set to squelch, so it means that the RF would have to be a particular level before it would break through the squelch. The average level, you've got a selection of 1, 2, 3, 4, depending on how tight you want the level to be. The weighting, you've got, so basically under the weighting you've got auto, peak, RMS, square root RMS, or plus or minus peak. So you've got that capability there as well. 750 microseconds for the FM de-emphasis or none. So we'll have a look at those in a moment, and there's some filters as well which we can have a look at. So I think we're pretty much good to go. We would have an audio tone through the speaker. We'll just turn the volume up on the speaker, ready now to connect our antenna. Obviously, if you're using an external antenna, be it whatever, discone or a folded dipole, a collinear, long wire antenna, that kind of thing, then obviously you're going to enhance its capability of receiving off-air signals. I would go as far as saying that the sensitivity on this port is in the region of a few microvolts, probably 3 or 4 microvolts. So if you wanted to really pick out, use the test set as a scanner receiver, which you can do, as a tunable radio receiver, then you would probably connect here a low noise amplifier. We're probably giving around about 20 dBs of gain across the frequency range of the instrument, and that will then increase the instrument sensitivity probably round about to 0.3, 0.2 of a microvolt, which would make it comparable with just a standard radio transceiver's specification. So that will give you that extended capability to pick up more distant signals. And seeing as the test set can also receive SSB, lower sideband, upper sideband, CW, AM, FM, can extend those functions into that area where we're using that in the sensitive receiver format. I've got with me today, just for this experiment, just a standard whip aerial that's you know, collapsible, so to speak. So we'll use that. I'll pull it out, we'll just connect it up now and see what happens. I might have to move the aerial about to get the best signal. Oh, there we are.
I'm good, thanks. Making any friends yet, he asked. Absolutely not. He frowned in the direction of the fresh vegetables before speaking again.
So I can select best range here, or
You could
amplitude.
come around the house tonight if you want to meet people. Some of the gang from work were there. That sounds nice, she said. You'll have to mind me.
50 kilohertz per division. 10 kilohertz.
Rise was a semi-detached house with
Time.
a projecting left half of the facade in red brick and the right half painted white.
So then we can look at the mod in more depth.
Red wine. She rang the bell and waited. A woman about her own age opened the door. Behind her, the hallway was bright and noisy.
So obviously, you know, I'm picking up more of a signal than the aerial is in this case.
Come on in. I'm Danielle.
So basically, if I put the 750 microsecond de-emphasis on, you can hear the audio. It's at full volume, but it's not particularly. Probably if I reduce the amplitude.
Danielle asked Alice if she wanted a glass
There you
of
go.
wine, and Alice said sure. Another man came over to open the fridge, gesturing in her direction.
Let's with it off.
He said to Felix, "Who's this?" "This is Alice.
Then
She's a novelist."
we've got,
"What's your name?" the man asked.
for measuring the signals
Upload it to
here,
Google.
we've got peak.
Alice
So then we can
Keller,
obviously
she
measure
said.
the peaks.
The man sat down on an empty chair
RMS.
and started typing into his phone.
Square
Alice was
root
drinking her wine,
times
gazing off
RMS.
around the room as if uninterested.
And then plus or minus
Hunched over his
peak,
phone now, the man said, "Here, she's famous.
or auto.
She's got a Wikipedia page and everything." Felix slid off the countertop and took the phone out of the friend's hand.
You've got a choice of D-mod off, so obviously that cuts it off, so you can't hear the audio. Then you've got on,
For the next time you go on a
and then
date,
squelch.
mention in a conversation that
Now in the on position there, what happens is if you disconnect the aerial, so there's no signal, just noise, then you'll hear the white noise permanently, which could get annoying after a time. So better to leave it on squelch unless you're dealing with really weak signals.
And then he shook his head and said,
So
"You're weird." And you could
one of the other things that you can do as well with this, naturally you can change that to an AM station if you want SSB, etc. So you would just do the same through, if you wanted to receive SSB off-air signals, you will go back to the main menu, select SSB, and then basically, I think in this case, yeah, it's trying to decode lower sideband on the FM signal as well as upper sideband. So basically, you'd input an SSB, well, a radio frequency where we've got an SSB transmission on it, and then it would naturally pick that up as well, which is quite good. I think there's a medium wave station near where I am, well, in the UK anyway. I think it's on 909 kilohertz. Set RF 909 kilohertz, and then we'll need to change that back to AM, obviously, to receive that. So if we go back to TX test and then D-mod, let's just see whether I can set that up. Oh, under RX test again, because we need to set the test set effectively for AM. So if I just put something like 60%, no matter what percentage you put in, as long as it knows it's AM. Then when you go back to TX test, then it'll change it to AM. So near something, not particularly strong. Now what you can do now to change this into a more tunable, usable radio receiver is you select set RF again, so you get that little arrow next to it, and then what you do, you press the VAR button here, and then you would set up your increment. So each notch on this rotary control, or the up down, would mean that it would advance by that step, which you can enter in. So I'm going to choose I'll choose 1 kilohertz just to be funny. So we'll have 1 kilohertz. Now each time I move that, it's obviously going to jump 1 kilohertz. So I'm just going to have a tune about. You can obviously change the bandwidth as well with the filter. So once you go into there, you can go down to your filters. So you've got 300 Hz high pass filter, speech band, photometrically weighted filter, and then you can have an external filter if you want as well. So now if I go to set RF, tune about, you see. I mean, in the workshop here on this little area, it'll be picking up all sorts of interference from switch mode, power supplies, test gear, lighting, you name it. Really needs to be plugged into an external antenna. So I'm not sure if I'm about to pick up Shannon Vormet up actually on SSB 5.0. Oh, sorry, it's 5.505 megahertz. Might be able to pick it up, but that's on SSB. But it's a very weak signal here anyway, so I might not be able to get it unless I put a low noise amplifier on here. No, I can't hear anything. Amplitude. Just put in receiver. Variable. Oh, why won't it let me put a variable in on that then? Oh yeah, there it has. Then the frequency, 5.505 megahertz. Do you know something? 5.505 megahertz. See what we pick up, if anything. And if that's AM. Yeah, I think it is. 8 megahertz, this might have something on it around about there. But yeah, not picking up much really on the HF frequency bands due to the you know, obviously the interference we're getting in here. It's quite a lot of interference, so just put that back on. Go back to RX test, set that then to FM on, and go back to TX test.
Not to worry, I won't. He put the phone down on the nearest corner of the bed and finished undressing. Eileen lay with her eyes closed.
Right, so if I go to variable there and set that to 100 kilohertz on there, then obviously tune around. So
this evening, and also classicfm.com. Getting in touch. We're saying hi to Larissa, enjoying the music, working on a late night PhD, but a researcher on Dickens. Just enjoying a moment of calm as she works her way through the night. And Heather's message from Newcastle.
so yeah, it's picking up quite well. Obviously we've still got distortion, signal to noise, measurement capability there if we were using that, filter.
Charges to go with it, and somehow too many memories, you just can't part with some things.
Oh, the other thing that you can do as well is you can change this to bar chart. So basically, if you go to config under the main screen, config and bottom left, and then there's this feature here called zoom. So you can select that. Now when you go back to TX test, now you'll get that, you see, you'll get the bar charts there. So while you're listening to the mod, so that's now reading that. That's quite interesting, you know. Gives you some bar chart examples, peaks, plus and minus, then obviously distortion, power, if you're reading RF power going in there. So one of the advantages as well to this, which is really useful, especially when you're fault finding on circuits within a radio transceiver such as this, for example, when you're trying to fault find on low level signals like reference oscillators or say for example synthesizer outputs that are very low in level, they're probably sub, you know, neg 100 dBs in some cases when it's loosely coupled, you can use like an RF probe, a pickup. It's just basically a piece of coax with a loop at the end, so you can sniff around the circuit inside, particularly on TX exciters, RX injection for the mixer, the reference oscillator, synthesizer, local oscillator output, things like that. You can sniff all these signals, and because the port here is very high sensitive, it means that when you're trying to fault find on radio equipment, it makes it really easy to be able to know if signals are there without directly coupling a coax to the active component, because obviously that can introduce other problems such as DC bias if you're going onto a collector of a transistor to measure its signal directly. So just to know whether that signal's getting to the transistor. And like in RF power amplifiers as well, you've got the base and the collector on a power amplifier transistor, then basically you can, without having to affect the impedance of the device by connecting a coax directly onto it, which people do, and have those issues where potentially you've got a potential overdrive situation coming in here because the RF power that you're looking at is to excess. All those sort of scenarios, and it affecting the tuning of a circuit as well, all has a direct bearing on how you do the measurement. So by this port being ultra sensitive means you can just get a coaxial cable with the loop at the end very loosely coupled and just sniff round inside circuitry. So it makes it a really useful fault finding aid, especially when you're dealing with sensitive, very high impedance circuits in RF applications where a 50 ohm load across it by potentially soldering a coax or whatever would then suppress that signal violently. So that is a really good fault finding aid. Very nice feature is that, and I think it's quite good at a receiver, and obviously can turn it into a tunable radio receiver as well. Really, in this context, I'm not showing it to its full extent because obviously we're just receiving a signal on a whip aerial here in the workshop, which is not the ideal of situations. But that connected to an external antenna, make no mistake about it, turned that into a very good radio receiver indeed, and an excellent piece of test equipment for that capability. So that's a little rundown of that. I don't think there's much more I can show you with regards to the sensitive receiver option. Obviously we've looked at the zoom capability there. If I switch that off and then go back to the TX test, then we get the scope back. I'm not sure if it's possible, but I haven't not sure if I've looked at that there. Under the scope you can select your source, so be it whether it's mod external, AF, in other words through the AF in on here, that one, or you can have DMod repeat, or DMod or beat free, because obviously for the CW, USB, LSB modes, and then distortion. So I don't know what the source fix is here. Oh yeah, I think you can just fix it so you can't change it, but I'll leave that at source auto. So there's quite a bit to it. Obviously I think you can decode still off the RF carrier, and that's also another feature that you can go into as well. The fact that if you go to change that to decode, it's currently set to ZVEI for cell call, but I think that if you go into the tones bit prior, obviously you can read CTCSS directly off a carrier by putting the filter on, and once you put the filter on, the 300 Hz filter or whatever, then you'll be able to pick out the CTCSS tone on a transmission. But insofar as the other features for its encode decode, yeah, I think you have to set that up first. So if you go into tones, and then you can select what system that you're wanting. So for example, we've got all these systems here, including CTCSS. There's obviously for Avionics ATIS as well, VDE, etc., ID. But you basically got DTMF, so you can read codes, telephone patching codes where people dial DTMF tones to access PSTN phone lines, things like that through radio systems. We've got all these different signaling standards, so you could put it onto a signaling standard, particularly if you wanted to read cell call transmissions from a radio system off air. As long as you select the right tone standard, then it'll decode it under the TX test, and this field here then where it says ZVI in this case, that will change to whichever tone standard or system that you've selected. So that's quite a good feature really. It's a very good little thing to do. Obviously there's a spectrum analyzer function. I think so if I go to spectrum analyzer, now we can look at the signal off air from obviously that radio station. So you can obviously set the center frequency. In this case I'll put it at 101.1 megahertz. We'll select input 2. So as it's scanning through, you'll hear it. Just pick the signal up. There you are. So you can look at the signal there as well. off air, and obviously if you put it at 0 span, you'll be able to hear the audio as well that's permanently on the spectrum analyzer. So you can use the spectrum analyzer function as part of the sensitive receiver too. And obviously if you widen the span up on the spectrum analyzer with the antenna signal being fed in here, then you're able to see the RF spectrum with all the radio signals and channels that are there. So I could change the span in this case, for example, to say 20 megahertz, and then obviously now we'll be able to see all the radio stations that are adjacent that we're just receiving off this little whip aerial that's plugged in here. So as you can see, it's all there. So it's quite useful, that. Obviously it's a bit like a band scope in that scenario. So a very useful feature indeed. So anyway, I think that's a complete rundown of the sensitive receiver function that's on these test sets, and a very useful feature to have. So to continue on in the theme of the sensitive receiver test, ROHDE and SCHWARZ do this cover which goes on the front of the test set, and it's metalized, obviously metal, and then we've got an antenna socket in the middle here, which has been built into the test head. Now this is the antenna here, which is held in this captive bracket, which is quite useful, you know, obviously for it's a very long aerial. It goes out around about, well, I'd say a good 1.5 meters, something like that. It must be about 12 section collapsible, something like that. So it's quite a lot to it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's about 10, 11 sections to it. And it's a nice quality antenna with a nice pointy thing at the end, you know. So, and then here we've got all the cable, so we can remove these catches like that, and then take this thing out, and then we've got like the spool of coaxial cable. So we've got one end which has got an N-type on it, which goes to the test set. Interesting enough, it's an N instead of a BNC. I would have probably expected to use a BNC to N-type adapter, because obviously the sensitive receiver port, unless using it very local to something, then obviously it might be able to pick up on the N-type. Then on top of that, we've got, when you unravel it all, I think it's, where is it now? Oh, there it is, look. Right, we've got this connector here, which then goes on, rather funny connector. It's like a weird sort of thing, but anyway, that goes onto this connector here. So obviously that screws onto there like that. Okay, and then what happens is then this effectively is a ground plane, is this metalized thing, so it picks up a better signal. So you put that on the ground, and they've obviously thought of that. They've got these little feet and everything, and then your whip aerial screws into here, you see. Quite clever. So then you have like a ROHDE and SCHWARZ antenna with a ground plane, and obviously then you know, we will then extend this out up to the heavens, and that would then give us basically our receiver. So that's how then we can obviously link it to the sensitive receiver on that, and then pick up off-air signals. So that's quite clever. Quite an interesting design, actually, you know. Although I am a little bit sceptical of the damage that if you don't put the items back in the casing properly and they're loose, because you've not fastened those catches up, these catches, what can happen is while you're obviously moving the test set or transporting it, etc., these sharp metal things can obviously hit the screen of a test set. So all these metal bits here can probably mark or damage the screen or the buttons, you know. So you've got to be really careful that when you pack it up, that you make sure that it's well and truly. What I do when I pack this test set up in its bag, I have a piece of cardboard which goes between this, because believe it or not, these lugs here, you see, for capturing the antenna, are facing the screen of the test set, these metal things, and plus this bit, so and that. So I always find that a little bit, you know, bit sketchy. So I always put like a piece of cardboard over this when it's plugged onto the front of a test. That way, yeah, I suppose it's something that ROHDE and SCHWARZ had thought about. It would be unlikely these lugs would move in transit, and it would keep that away from the front, but I just don't like it, that's all, because it's just too much of a risk of that happening. Especially if, for example, one of these connectors comes away from its spool and starts flapping around between the screen and this, it could scratch or damage the screen. So just, you know, just mindful of that. But yeah, clever design, and with the fancy whip aerial as well. Well made. It's a very heavy, good quality antenna. It's not one of these thin cheap rubbish things, you know. It's very good quality, I must admit, for ROHDE and SCHWARZ. So obviously built to last, you know, with the ruggedized front. So now what we've got is this remote control unit here, which plugs into the back of the CMS. This is meant for auto test, in particular for when we're, you know, running automatic test procedures, using the program for the ILS, VOR, marker beacon, all the other bits and bobs that we can put in there, or we can program it with particular things. So your mic tell, so it can test, for example, on aircraft, avionic intercom systems and things like that. So you can press start on that or accept. There's all sorts of different things that you can do here, and then it'll then initiate that then on the radio test set. So depending on what obviously you've configured, then it'll go through that now, setting all the parameters up, and obviously commencing a test of the system. So there's all sorts that you can do with it. It's quite a clever little piece of kit, but obviously once you define the program that you've got on there, then obviously it will, you know, it will run that auto test. So you can define the program that you want to run, and then basically it will then go ahead and run that. So you can program the test set with your run sequence beforehand. It's saying initializing, it says auto test wait, clear or enter. So I'll just accept on that, or enter. There we are. Auto test run, VOR test. So it's initializing the test sequences now for VOR, and going through that once we've initiated that VOR test, which I've just done. So it auto configures the test set, you see. So I'll press enter on that. Auto test run all, so then it'll obviously check for certain parameters or responses back, obviously using the audio cables, RF cables, etc. So it'll be looking for feedback to come back, and then it'll hold each time it does something, ready for you to confirm the next step as well. And then each parameter, 60 degrees, check for this, you know, and it gives you the instructions as you go through it. So it's quite a nice little thing. So that's that really. There's not much else to explain about the remote controller, but obviously if you define a user test, there's not much to it. There's just like a just sort of a standard box sort of thing, and you've got your telephone handsets and things that can plug in there, so you can test those individually as well. So quite a useful little box. But the cable's about 5 meters that comes with it. So as it says in the service manual and the instruction manual, that you can have instruments sat in the cockpit of the aircraft, and then use this then while you're sat in the pilot seat, co-pilot seat or whatever, to then do the auto test to check the instrumentation on the aircraft. So that's quite useful. But I dare say you could put other programs in as well that's non-avionics, obviously. I store those in the test set and then select those auto test routines to run from this. So it's fully configurable, as just because it's in this case used with avionics programs that are stored in the CMS33 doesn't mean you can't make up your own programs for testing PMR, ham radio, marine radio, other types of radio systems as well, and then you can select the test sequences here and get those to run as well, you see. So it is more wide reaching than just avionics, obviously. Okay, so that's that. Okay, so ready to do a measurement now for VSWR using the VSWR bridge and the power measurement capability through the VSWR insertion unit. This is obviously used in the facility of connecting to a base station antenna or a vehicle antenna, aircraft antenna, ship, boat radio antenna, etc. And this will measure VSWR forward and reflected power as well as voltage standing wave ratio. So that's quite important for obviously when we're tuning antenna systems in, checking faults on coaxial feeders, antennas, things like that. So this will reveal a fault with a base station antenna up a radio mast where we've got an antenna mounted high up on a tower or on a vehicle or wherever on a property. So that will come in very useful. Now this particular unit boasts a frequency range of 70 megahertz to 1 gigahertz, and it also I'm not sure what power handling it can take. The Marconi one can take about 500 watts, but which obviously extends the instrument's power measurement capability, because you can use one of these in synergy with a 50 ohm load on one side terminated for measuring high powered radio transmitters as a way of being able to measure higher RF power that can be taken through the N-type socket directly into the front of the test set. So that's really useful for that facility as well. But in this context, we've got 70 megahertz, which is from low band VHF basically on the PMR, about 68 megahertz to 88 megahertz is low band PMR, so it'll probably pick up transceivers as low as 60 odd megahertz. But I think as far as amateur radio is concerned, 4 meters AM band at 70 megs will be obtainable obviously, and all the other AM bands upwards, but below that 6 meters, 10 meters, etc. ham bands at 50 megs and 30 megahertz bands will not be attainable. But there's probably an HF version of this, just like the Marconi variant of it. It's a nice little compact unit. It's just got a data socket here that connects to this cable. So what we'll do, we'll plug it in and we'll see what happens. It should auto detect it, and I'll just plug this cable in. There we go. So we've connected that up, and now it's converted the screen to read power forward and reflected. Now when we select these menus, we obviously get the down arrow as well, so there's other functions available. So just briefly show you that. So there were like peak envelope power settings and things like that are available, holding the peak power and such like, so that they're options that we can select. There's a legend on here showing that this is an input with the arrow facing in, whereas on the other side there's no legend, so obviously that's the output. So we'll connect our radio transceiver up now to the N-type plug and get that on, get that there, and then we'll just connect the termination on. Now I've got an RF termination for a perfect match as well as an RF attenuator, which we can leave open-ended, so we'll get some reflection coming back through the power head. So if I key up this transceiver now and take notice of the frequency, because obviously that's not, I don't think that'll be applicable in this case because we're not reading power or frequency through these connectors. It's in here, so it won't read the frequency, I don't think, on that, but it'll read power. Obviously a forward power of 19.86 watts and a reflected power of 0.5 watts from this load, and obviously I'm just moving that around and it's changing its characteristics a little bit, so might be got a dirty connector or something like that on the inside. So that's the VSWR reading there, and so that gives us that reflected power. Now obviously if I remove the RF load altogether, then we should get all the power coming back, not just a proportion of it. So the RF signal gets to there and it can't go any further, so the only way it can go is back to the source. So if I key up now, we should be more or less getting about the same, yeah. So the reflected power is more or less in synergy with the forward power. And obviously that's not good for the radio, so I've just unkeyed it to protect it. Otherwise it could damage the radio. So what we'll do, we'll give it a better match, but still not a perfect match. We'll use this attenuator that I've found. And we'll leave the end of the attenuator open so that it provides some RF absorption, but not wholly. So if I key up again, we've got obviously some forward power, but also some reflected power. So the VSWR is, you know, quite high on that. It's 20 to 1 VSWR. VSWR in this case is measured in a ratio of whatever the figure is here to 1, obviously. So if it's normally, we need to get the VSWR as low as we possibly can on antenna systems. Obviously the lower the VSWR, the better the match is from the source impedance. So we could then, for example, get a VSWR ideally down to 1 to 1.3, 1 to 1.4 maximum, possibly 1 to 1.5. Any higher than that, the RF power reflected gets a little bit too much, and that then causes heating in the transmitter and then can cause undesirable harmonic effects, because VSWR is not just about being able to match the antenna with its frequency resonance to the transmitter. That's part of the reason, but the other part of the reason as well is to improve the efficiency in doing that. But furthermore, when you introduce reflected power back into a transceiver, it then induces undesirable effects such as instability, self-oscillation. It can even cause more modulation distortion because the radio is not behaving as it should. It can cause harmonic or intermodulation products to appear on the transmitter's output, which then can cause undesirable interference to other radio services. So there's lots of things really to consider when you're looking at VSWR. But naturally, in a vehicle installation, for example, we have a vertical whip on top of a vehicle, a truck, a bus, a car, a van, that kind of thing. We're looking at trimming the antenna length of the whip so that we get the minimum VSWR along with the ground plane in the vehicle. If we're on a marine vessel or something like that, a ship or a boat, we're again looking to tune the collinear antenna or match it correctly to the coaxial feeder, which will then result in obviously seawater ingress and things like that into antennas can cause problems, as well as coaxial cables which can corrode. If the plugs on the end of the coaxial cables, the RF connectors are not made up properly or not soldered correctly, or the braid of the outer touches the inner while somebody's assembling it, then the VSWR will obviously be through the roof. So it can help diagnose problems like that, or water ingress into coaxial cables or antennas. And also it can reveal trapped cables as well, where the inner and outer shorted further down the cable, and that in itself can lead to issues where, depending on the length of cable that's being used, you can get some weird anomalies as well with RF, where you can get multiple wavelengths of the cable. If it matches the exact wavelength of the RF that's in use, it can cause some weird things to happen. So that's another thing to always avoid with radio transmitting equipment, is cable lengths that match the physical wavelength of the RF signal, because then it can nullify the signal as well, and we get some really strange things that can happen there as well. It's quite rare phenomenon to happen, but I have seen it, and it does happen from time to time. So you can get that kind of anomaly when a cable is shorted at different lengths or intervals along its length. So in a building, if somebody's knocked a nail through a coaxial cable, where they're hanging a picture up or something, and it's in a bit of conduit behind a plastered wall, that nail goes into the cable, outer jacket, the outer braid, and into the inner, then it can cause massive problems with regards to trying to trace that fault. Because at certain frequencies, that will be multiple wavelengths of the transmitter or multiples of it, and it will not give a high VSWR. But yet when you put an RF power meter at the coaxial cable end of the antenna, there'll be no RF power there. And so that can also present with some strange issues in trying to find that. And that's where we'd use a distance to fault measuring capability, where we can use a tracking gen on a spectrum analyzer to find the distance to fault. And some of these testers like CMS33 I'll be demonstrating that has that capability on it, as well as other Marconi instruments and things where you can find coaxial faults quite easy down to millimetric level. And it's something that the microwave test set does as well, the Marconi 6200 series, where using the reflection bridge you can actually find a discontinue in a waveguide or coaxial cable. So we'll do more on that in other videos. So yeah, really good good little thing. You know, obviously quite a very useful measurement device. Obviously we can use it for SSB transmissions, AM transmissions, as well as FM transmissions as well, or any other type of transmission, even digital transmissions it can read forward and reflected power just like anything else. If you want to know more about RF power measurements and power meters in particular, I have a large selection of bird RF meters, and I did a video which is on my YouTube channel where it shows the bird series of RF watt meters, and indeed there's one there that measures what will be P25, Tetra, DMR, all the different digital transmission modes as well as analog. So if you're interested in that kind of thing, please head over to that video. Anyway, that's that. As you can see, it's fairly straightforward when it's connected into the rear of a test set, and then to that converts the screen. We get other options as well, which I've just briefly shown you, and then obviously when you disconnect that cable, then it'll revert back to the previous screen that it was on before. So nice little feature. Okay, one of the other nice features about the receiver testing side of things, which applies to SSB radios as well as AM and FM radios, is as we've been discussing so far with the tests that we've currently shown in this video, as we select a field, then we get an additional down arrow which appears here, which gives us access to then the other secret menus that lay behind the primary functions and test functions. So one of the little tests that we've set up here is we've got a 934 megahertz radio along with its speaker and RF and AF loads, which then the audio out is connected to the AF in on the radio test set. We're generating our signal out of here at 934.3125 megahertz, which is the channel this radio's on. What we're going to do is we're going to do a test to test the parameters of a squelch, which is a nice little feature that these radio test sets have. So if I go to RF level, obviously we've got a down arrow. Set a down arrow. We've got three different functions here which we can now select. So one of them is bandwidth measure, squelch measure, and then quieting. So these are three different separate tests that can be done. So as an example, I've got this radio set up at the moment where if I just turn the squelch down, so that's the squelch, I'll just get the radio to squelch. Now if I select the speaker so I can hear it here, yeah, it's there as well. Yeah, I'll switch the speaker off. Right, so I set the squelch to a particular level, whatever that might be on the radio, and I need to know what that is. Now some radios don't have an independent squelch control that's user settable. It's settable in the radio on a potentiometer. Depends what kind of radio transceiver it is, but in this case I can manually control it. But what we're going to do, we're going to get the test set now to perform an auto test of the squelch parameters, and it'll measure that automatically. And the way it does that is it ups and downs the RF level in synergy with modulating it with a 1.5 kilohertz deviation at 1 kilohertz tone frequency on the RF carrier, so it detects it, and then it adjusts the squelch until it obviously squelches out the radio, and it measures that parameter. So it's got to get audio feedback through this socket, otherwise it won't work, from the speaker output of the radio or the AF output from the radio. So here goes. We'll set the squelch limits, and off it goes. So as you can see, it's just in the RF level. It's found the point where the mute's open, and now it'll finally adjust around that to see what level the squelch will open at. Then it'll come back with a parameter. There we are. So then it's giving us that parameter there. So in this case, where that squelch level was set to, it was set to 0.32 microvolts, and it had a 0.3 dB hysteresis. So that squelch level is then measured there. So that's quite handy, that, if you're wanting to know what the squelch spec is. Now I've increased the squelch spec there, so let's do it again, see what it finds this time. And this is something you can, obviously finally adjust. So this could be defined as part of an auto test procedure as well, where you're doing conformance testing on radio transceivers. So it'll do that there. So again, now it's found the a 1.1 microvolt sensitivity at 0.1 dB hysteresis. So the hysteresis is quite tight on this, but the squelch level, obviously we can adjust the RF level that's being received by the radio. So that enables us then to measure the RF performance of the front end. This is in addition, of course, to the standard test procedures, which is signal to noise and distortion. So if I open the mute a second, we've got a SINAD, and currently that's reading 17.5 dBs at 1.83083 microvolts. So if I were to adjust this, it might say in the service manual, but it's 12 dB points, got to be better than 0.3 microvolts or something, So it's 13 dB SINAD there, and then as we're reducing the RF level down, I think it's 12 dB point is around about there, 0.396 of a microvolt. So if we wanted to better that, we'd tune the receiver front end on the radio to give better performance on that. Try and maximise the SINAD at that RF level or lower. But its sensitivity is quite good, actually. I mean, it does go way down. Or it would technically mute out. So if I switch the RF off a second, set the mute to there, about there, then put the RF level on, it's quite a good, sort of talking 0.3 microvolts, which in dBm level, if you work in dBms, about neg 116, neg 17 dBm, neg 119 roughly when it squelches out. So that's pretty good. And also we can measure not only that, but we've got distortion measurement as well. So if we want to look at the AFPA stage coming out the radio, we can do that too. And then obviously we've got distortion. Part of that, we've got a filter as well, so you can select your different filter options. So you might want, for example, to just look at the speech band and get rid of all the other stuff, which will then obviously affect the distortion measurement as well and improve that, as you've seen there. And likewise, we can then put a phosphometrically weighted filter on as well. Again, that will improve everything all around, including the SINAD as well. So yeah, we've got 25 dB SINAD. So there's all these different filters and things you see that you can select. All good stuff. So that's a little rundown of that. Obviously there are other tests as well that we can do under set RF level. I think under set RF or something under there as well. Notch. We can have I don't know what this test is. So that'll be probably for the SSB notch testing or something. Notch filter at 1 kilohertz. So you can select a notch filter. So there's different things that you can do. Raison, width, notch. So there's quite a bit to it. You can do RF level. Again, there's another parameter there. Oh, AF level, sorry. So yeah, there's quite a bit there. Another filter. Oh, that we've already looked at that. Synad. Again, there's another down arrow there. So window level search. So you can click continue. So you can see there's quite a lot. AF couple, average level. So these are the averages for that level. So there's quite a bit, as you can see. Go really into refinements there as well. That signal to noise, where it turns the carrier mod on and off. And again, Gen 1, Gen 2, further options there. So yeah, very good. Put Synad back on. So that is a quick demonstration of the sort of auto test routines that you can use on the CMS33 for the receiver testing, and that's even before we get into the main test that for the Avionics side. But yeah, so you can do all this testing with it, so it's really good. I think on the TX side as well, I think under there, followed by that as well, duplex space. Let's have a look here. Frequency preset, is that adjacent channel power or something? I think it is. Necessary system option not fitted. Frequency trans, what's this one here? Distortion. Input 1, input 2. Not sure what that is. So yeah, there's quite a bit that you can do with it. Quite interesting. So that's the end of that. Okay, well, the technical manager approves of the ROHDE SCHWARZ CMS33 radio test set, and he's given his seal approval for this instrument. So I'm just looking at some paperwork now. I noted some, hopefully it'll help somebody. Not only have I provided that drawing which detailed the RF attenuator values of resistors for the pi attenuator for the low power port, but what I also did is I did a drawing with the module numbers on them. So what we've got the part numbers, if you like, for the CMS33 modules, which is the ones that we were looking at internally. So they're the ROHDE SCHWARZ part numbers. Now I'm going to be looking at the CMS34 radio test set again that I've already previously featured on this channel, because I'm going to be reaching out to ROHDE and SCHWARZ for a second time, and hopefully they'll get it right the second time. I'm going to give them a chance. But as part of that repair video that will be upcoming for the final slog with ROHDE and SCHWARZ CMS54 radio test set, I'm going to compare those module numbers against what's in the CMS54. Now we've also got a digital board there and an RF attenuator section as well, so I think they're very similar part numbers, if not the same, to what will be in all the CMS range of test sets. Now one other thing that I would like to say as well at this stage is that that information that is commonly available, the service manual on the internet for servicing CMS's radio test sets, seems to be aimed at the CMS52 model of radio test set, and they're not the same, unfortunately. There are slight differences in some of the modules that are used across the test sets, I think there's some commonalities between them, but I think there's also some slight differences. I looked at the circuit diagram on the CMS33 radio test set for this X604, which is the BNC connector on the front, and I noticed that on their drawing the values of the resistors were slightly different, and this capacitor was not before the pi attenuator but after, and the layout on the PCB as well for the components is just different, only marginally different to the modules that's within the CMS54 and the CMS33. I'd say the CMS33 radio test set, from what I can remember, the RF module we had apart to get this information here, the input-output module, it's the same as what's in the CMS54, because I remember the layout quite clearly with the resistors. So we'll when we do the CMS54 video, which is upcoming shortly, after I've reached out to ROHDE and SCHWARZ and tried to get them to sort out the customer service for ROHDE and SCHWARZ UK and give me some help, then when I strip that test set down again and make another video, we'll compare these part numbers of these modules. Now, what I also have is quite a lot of other broadcast ROHDE and SCHWARZ test gear, which I'm going to be featuring on this video, on this YouTube channel, which is aimed at the RF broadcast market for digital terrestrial television, analog television and cable TV networks as well, for some of the large broadcasters. Now, I've noticed that when I've taken the covers off those, which I haven't featured on this channel yet, but they are upcoming, believe me, the modules inside those are the same as what's in these. So there may be some common parts there that, that can be used or cross-fertilised into other test sets. So that'll be an interesting exercise coming up. But what I was going to say about this RF attenuator section, if you get a test set, it doesn't matter if it's CMS 50, 52, 54, a 33, whatever, if you didn't know that information, then what you can do is, if these resistors have all burned out because somebody's fed a load of power in, is you can just literally bridge this resistor here that's burned out, obviously remove these two so there's just a straight connection in. If you've then repaired what's after this, be it a mimic stage or a gas FET amplifier, whatever stage that then reads the RF level after and obviously amplifies in several stages before it's analysed. Once you've done those repairs and got that sorted out, and the remaining thing is this RF attenuator, because as I say, the resistor values are written on the actual surface mount resistor tops, and if they're burned up then you're not going to know the value. And as I say, the difference between the CMS33, the CMS54 and the CMS52, this resistor chain here in the pi attenuator is different values depending on what model of test set it is. Because I think if I've got the different RF modules in them, then they'll have different gains, they'll be from a different revision, a different series, if you like, of revision. So there are slight design differences with some of them. So I think in that case, the best thing to do is to link out the resistor at the top, so it's just one continuous connection to the capacitor. Assuming you've got the rest of these stages up and running and working, put a level in, say, I don't know, 0 dBm as an example. It could be -20, it could be any level, but stick a level in there. And when you go to Spectrum Analyser on the test set, and you obviously select Spectrum Analyser, when you're reading the level on the Spectrum Analyser and you put the markers on, then basically whatever level that is, if it's a 30 dBs higher, reading 30 dBs higher on the Spectrum Analyser than you're entering here, then you could make yourself then, that you need to produce a 30 dB attenuator. So you're sort of reverse engineering it. So that's what I was going to suggest, that anybody who's got that problem, it's quite easy just to link the signal straight in, so there's no attenuation. Stick a SIGGEN on that BNC port on input 2, and this doesn't matter what CMS range of test set you've got, and then just inject a signal. Obviously the difference in level between the signal coming in and what you're reading there will be the positive gain, and so therefore the difference in dBs equals whatever the value is for the attenuator you need to produce. And these are quite easy to build with surface mount resistors. The only thing about it is certain attenuation levels you've got strange values, but you can make those values up by using resistors in parallel and make those possible. But you can build then, say if it's a 30 dB difference between what you're putting on the BNC and what's read on the spectrum analyzer, as in a 30 dB positive gain, not a loss but a positive gain obviously, then you know that everything's working fine. You just need then to choose a 30 dB attenuator and then put that in. So but yeah, I mean, I've never understood why they did that really with these resistors, because they could have just put a BNC to SMA adapter there and then used one of the if you watch my attenuators video, there's these little SMA to SMA RF attenuators that can stand a couple of watts anyway. So they could have made the test set higher specification by adding a little cylindrical attenuator, and that would have then solved that problem, because basically you would have had a situation there where you've got an RF attenuator that's rated to a higher power that would naturally have provided a better frequency response and higher power rating across its range. And it could just be down to costs and things like that, you know. Maybe ROHDE and SCHWARZ were a bit tight, stingy with the cost, but that's the sort of thing I'm thinking of, where you've got an RF attenuator that can stand a watt, 2 watts, SMA on one side, SMA on the other. That can provide whatever dB gain you select. Okay, so finally a look at the rear of the instrument. We've got the on-off switch here, rocker switch, where you can select between mains, power or battery, which is provided on this socket here. Quite a common connector that's found on these test sets. It's almost like an XLR. It probably is actually. It looks like an XLR to me, but it may not be. It might be a special ROHDE and SCHWARZ thing, but it looks like an XLR. But anyway, we've also got a mains fuse here to protect it, which is just barely seeable. It's just in that corner down there. If you can just see that on the camera, it's barely visible. And then going down, we've got a voltage selector, which is quite important obviously for international markets. IEC mains input jack. We've got the heatsink of the power supply, which never really seems to get hot at all. It's just lukewarm. Then we've got the fan here, or the ventilator as ROHDE and SCHWARZ like to call it. This socket here is for the VSWR bridge, which we've looked at earlier in the video, and these are where your mic telephone sockets for things, or telephone handsets, microphone handsets can plug into directly for testing, audio testing. We've got a GPIB connector. This large D-type here is also for use with the remote control head that we're looking at earlier, and then the bottom one is remote control. So I think it's tells you on and what they are. So if we just zoom in, they control both of these, and that's GPIB, but that's basically what these are. Now you'll notice as well on this test up, the only thing that I think could have been improved upon, there's no composite video output. Don't forget this test set was produced in the days before VGA, SVGA modes were commonly accepted on radio test sets as being available from the rear panels. Marconi instruments tended to have that right at the early onset, really, early 2000s, late 1990s, early 2000s, when VGA standard was more being accepted on radio test sets, SVGA outputs, things like that. And also on the HP Agilent range, a lot of the spectrum analyzers and radio test sets like the HP 8920 AMB models, 8922, etc., and spectrum analyzers had composite video output and a BNC on the back. and obviously you can get composite video adapters to HDMI or VGA these days, so you can use modern LED LCD monitors with those kind of instruments. Unfortunately, on the ROHDE and SCHWARZ, they didn't seem to consider the fact that yes, there's no video output on the back, which sometimes, if you've got the luxury of having other screens and things that you can display the image of the monitor on the front on it, it makes it quite a good instrument then for you know, presenting on, and in a classroom environment or teaching environment, or even just so that you can see the screen a lot better. And also, if a screen ever packs in or goes faulty, and you can't get a replacement, at least you still can get the image displayed remotely, so it makes the test set more viable even in that kind of condition. Unfortunately, as I've said, there's no video output on the back, so you're entirely reliant on the LCD screen always working. We've got some chunky, very chunky, like feet on the back to prevent damage. We've got a cable stay, so we can wrap the cables round as well, which is a good thought of ROHDE and SCHWARZ. Keeps things nice and tidy, and all in all, very nice, nicely presented. On the rear, on the side, we've got a carry handle, and then the loudspeaker is built into the side as well, just behind there. The DMOD outputs on the front as well, so whatever the speaker picks up, there's a BNC on the front covers we looked at earlier that carries the DMOD output. It's all well made, very well made radio test instrument. All proper metal, no plastic, fantastic, anything like that. The only plastic bits on it that are a bit of a problem are these feet, which fail unfortunately. They break off, particularly if the test set's handled you know, with a bit of roughness. I don't quite, yeah, these catches are a pain in the backside. They're okay, but they tend to cause more trouble than they're worth, these things. So I'd have preferred if it had just had a different way of clipping on the front cover rather than using these silly catches that tend to come unclipped by themselves anyway. So, but they've got a strap as well that you can fasten to these hooks at the side of the carry handle, so you can carry it. There's only a carry handle on one side though, because on the other side there's no carry handle on the other, as you can see. So it's just blanked off for some reason, I don't know why. But they've gone to great extent in making sure that, you know, it's as rugged as possible, and it's obviously hard wearing and very, very, very good little test instrument, really is. So yeah, that's it really on that. So perhaps in hindsight, had they not chosen the surface mount resistor path, which they've gone for here, where they're using sort of very low powered valued resistors, and you've got all this parasitic inductance and all kinds of RF leakage and various other things going on, capacitance all around there, it may have just been better just to purchase one of these, you know, a BNC to SMA adapter on the front of the instrument with that screwed on the back, and then a cable going off then to the module, and it would have probably saved money on other components and trying to make the circuit board more condensed to accept all these components, when you could have just had that on its own. And that is a repairable, replaceable part, so if it does burn out, you can just buy another one of those, readily available these days on most good auction sites, quite cheap, and then you can replace it. And so it's easy to do without the need of a circuit diagram, because attenuation is written on the outside shell, whereas the resistor values that are used here, unless you've got the circuit diagram, you're not going to know what the resistor values are. And as we all know, it's very difficult to get service information for ROHDE and SCHWARZ, so quite don't understand why they never went that way with these attenuators, but anyway, that's a story for another day. So yeah, all in all, very good radio test set. Fully recommend the CMS series of radio test sets. Nice and compact, quite funky little test set, very well featured and high specification, and well worth having. Nice little small radio test set to have on your bench. It's quite shallow from front to back, narrow width and height, and it's just nice and compact for a bench type setting. Whereas, you know, some instruments can be quite enormous all round and heavy and bulky and difficult to manage on the bench. This fits quite nicely and is a very good asset to any workshop. So if you do get the opportunity to buy a ROHDE & SCHWARZ radio test set, I fully recommend doing so. Just be aware of all the problems that we've highlighted in this video. As soon as you take precautions to mitigate against those issues, then you should be fine. The build quality is exceptional on ROHDE & SCHWARZ radio test sets. I mean, obviously they last a long time, fingers crossed, before they go faulty, and the capability that they've got is really the top end of the marketplace with regard to specification and features. So you won't go wrong buying a ROHDE & SCHWARZ radio test set. And I think when we look at what the capabilities are, this radio tester, what it can do for its size, I think it's quite exceptional. So to find something comparable on the market this physical size is quite difficult. So yeah, I think that's the positives really. It's a very user-friendly, very well made radio test set. I think the negatives are what we've covered already regarding repair costs and the difficulty in obtaining spare parts and getting customer service, positive customer service from ROHDE & SCHWARZ, particularly here in the UK, and having that help when you need it in order to get the piece of equipment on the road at a reasonable cost. So yeah, they're the sort of negatives really, the cost of ownership, whereas the positives are obviously it's an excellent instrument to have. So I think we've reached the end of this video now. I don't think there's any more we can sort of squeeze out of this radio test set. The technical manager is quite pleased with the test set. He gives his approval, and thank you very much for watching. If you like the video, please hit the subscribe button, it helps the channel. There'll be plenty more of these videos coming on ROHDE & SCHWARZ radio communications test instruments. We've got a selection to go through yet, particularly the broadcast fraternity. So thank you very much for watching, and catch you again in the next video. Bye for now.